Hello everybody, welcome to the very first video of the DeHavilland Beaver Flight Simulator Cockpit rig build. Yeah, that's a mouthful after saying that 5 times fast. I want to build a flight simulator rig build off the DeHavilland Beaver because it's unique, it's cool. I'm an old school person, I love old school cars, and I love a big old school radial engine just thumping out in front of you. It's just, it tickles my fancy. I know a lot of people will do the Cessna 172, 182 flight simulator rig builds, and that's not to knock you guys, that's cool, you do you. But I want to do something more unique and more adventurous, and I don't think anybody has ever done a DeHavilland Beaver flight simulator rig build before, so we're going to break ground and trail the blaze ourselves. Blazing the trail. I don't know English much. So this video is just concentrating on a 3D modeling for one particular piece, the Throttle Quadrant. The next part, part 2 if you will be printing it up and assembling it all, possibly polishing it up. And then part 3 will be actually how to program it. I'm actually using real throttle position sensors as my potentiometers, and I'm going to show you how to wire all that fun stuff up. That's in part 3. So I know that this video is 3 hours long, but I want to try this format and see if people like it or not. I want to try to inspire you guys to learn 3D CAD software and not just copy paste other people's work, and try to figure out and try to show you guys how you can come up with something unique for yourselves that you can possibly start learning on your own. And you don't need a 3D printer to start AutoCAD designing something right away. If you think, yeah, I could buy a printer someday, well, that's cool, that's awesome. It took me years to save up for mine. But for right now, you can actually design all your own hardware and your own pieces and see how they interact with each other. And OnShape is technically free. That's my CAD software. You can start designing this stuff right now. So I'm hoping I'm trying to inspire somebody out there to actually get off the seat and actually start engineering something for themselves. I really like it. It's been a lot of fun. A little bit challenging, but a lot of fun. So the first part of this video, I was just eyeballing the flight simulator, YouTube, and Google Images and trying to figure out how big everything is and the scaling and all of that fun stuff, how big things are. About halfway through the video, I finally bought the blueprints. Although they were incomplete, they were a big help, especially with designing the throttle levers and knobs. And we'll break out the blueprints later, and I'll show you a little bit more on how I took those numbers off and put them into the CAD software. That will be included as well. Now, in the second half of the video, towards the end, I found that my gain later was cranked up a little too much. So the audio might be a little bit weird, but it's perfectly intelligible. It sounds a little bit distorted because I was overdriving my mic, apparently. But I still wanted to show you guys the 3D CAD build. I'm a redneck hillbilly from the Pacific Northwest, so if I could figure it out, you guys should have a chance on figuring out this stuff too. So hopefully this inspires you. Just freaking get on that Spectrum train and just freaking lean into it and get it done. Right, let's go cross-eyed and design a throttle quadrant for the DeHavilland Beaver Flight Simulator Cockpit rig build. Whatever you want to call it. Let's begin. We need to bevy for this. This is going to be a long video. Okay, so we're in. OnShape is free. So this is how we create a 3D object out of nothing. Perfect. I won't show you guys per se on how to use this, but I'll show you some bigger highlights, and we'll probably do time lapses for the rest of the thing. I don't know. There's plenty of tutorials on how to use OnShape, so I won't bother all you with that. Let's just go ahead and start designing our throttle quadrant. Okay, so we're going to, let's see, I want the right or left plane. Let's do left plane here. I want to make a first sketch here. So then so let's go to here. You don't have to worry about our sizes per se. For our lines, we can always fix those in a hot second. What we want to do, be fairly generous. Let's just get, what we're doing is getting very rough shape. Okay, so this is going to be where the gauges are going to sit in, the manifold pressure gauge and the engine RPM gauge. So we gotta have to get this angle. You don't want too up in the air because you want to read it. So 3, I think. Let's just do the rough outline.
scrub it. And then this will be here. I can already tell that I did not make this long enough. 3-point arc here to here, and then that is more or less our very, very rough, very rough drawing, right? So if you jump back in the simulator right quick, now as you can see, the throttle quadrant. Now here's this other part. Putting this to scale is not exactly easy, okay? Now what I did is I put a gauge between here and here on my computer screen and simply figured out, okay, that's 3 inches. So if that's 3 inches, this has got to be 3 inches. So by the time you include these bolt holes, it's about 4 inches long. So you figure 4 inches, 8 inches, 9 inches, 10 inches. Pretty much figure this is a 9 to 10 inch wide console, basically. Get out of here, you're annoying me. So with that being said, if that's roughly 10 inches, that looks like halves. That could be at least 5 inches out. So total, I mean, you're looking close to this thing being a foot wide. Again, this is a very rough, very rough estimate, but let's try that and we'll just see what it looks like. So with that being said, we're going to have to define some. We need to define some measurements here. This is where we can fine tune everything up. So let's go right now, for argument's sake, let's just go 12 inches there. This, 4 inches maybe? Oh, how tall do you think that is? Oh, 3 inches at least. 3 inches wide? See, it's kind of hard in a simulator because everything gets scaled. At least 3, possibly 4. I'm going to say 4. I'm going to say 4 inches. Because there's more mass here than this, where this drops off. So I'm going to say 4 inches on the top. Well, already plugged in 4 inches. Yeah, numbskull. And then here, we have to figure out how much our protrusion sticks out. Honestly, 4 inches? 5 inches? Might be close to 5 inches. Let's define that set of dimensions. Yep, and here, and here. Let's go 5 inches and see what that looks like. Okay, that's... How much can we squeak? Sure. Now for here, let's dimension. Can we dimension this? I can't remember how this radius works. Can't remember how that works. Scrub it. Let's just delete. We'll just delete this radius right here. No. Let's just delete. So 12 and 5, so 9. So we don't have much for scaling right here. So let's do 4 here as well for now. And then we'll use our 3-point arc again. And see if we can't snap. No. No, it's actually this space right here. I'm more like 3 inches, eh? Yeah. Looks a little bit more righter-ish. That could, because by the time I start rounding down, it starts to round down within 2 or 3 inches. I mean, technically this whole thing slopes, but I'm not trying to get 100% perfect. I am trying to get it good enough so we have a 90-degree throw on our levers here, right? You know, I would say that's not bad. That's not bad. So let's go ahead and accept it. Let's just extrude this, basically make this into an actual 3D object. And we're just gonna click out 10 inches. Boom. So that's roughly, I mean, this is very, very rough shape, but this is roughly what we're looking at here. Okay, it's not bad. Actually, we could probably neck this down a little bit. Just possibly, I think a little bit less steep of an angle here. So we can go back to here, actually. And actually probably open this up to 4 inches. That would, no, that wouldn't quite work, would it? Well, let's go 3.5 on that. That looked not too bad. But I would like to expand this out, say like the 5 inches. I forgot to turn my phone off. Stand by. I want to go taller person. Well, how tall do you think that thing is? See, again, you kind of just have to... Is it as tall as it is wide? Yeah, that's a good 8 inches, possibly. What are... How tall is this thing? 10 inches? Let's do 8. I thought I shut it off. That's what happens when people aren't on your... Oh, no. That's way too shallow. No, let's do 9 inches. Okay. Do not disturb has been officially put on. Thank you, people. So, let's... Okay. That's not bad. It's not bad, actually. Can we just, like, put a fillet in there right quick? Let's try to put a fillet just to see how round this is. I'm kind of curious. We should be able to. Smooth this face out here. Right about there. See, look at that. Look at that. Yes. You know, we could put a dip in here. To cut that out a little bit. I'm gonna have to do some hawing and humming on that. But general shape, that's not too terrible. Yeah, let's go with that. Yeah, I'm fairly happy with that. Okay. Now the catch-22 is, do I want to do the sweep right here? I'm half tempted to say no, simply because I would like to put a 10 piece of metal on here, sheet metal, and do this labeling here. And I might have problems actually sticking to here. So I don't think I'll do the swoop bit. Some of the, as you've seen in the 53 one, so if we take a look at the 53 one, you see how it's nice and flat? So basically, we're going to be taking a whole bunch of different versions of the Beavers and making our own little hot mess express of one. But that's looking too bad. Okay, now I'm going to cut the holes for the Throttle Quadrant. I don't know why I got problems saying that. Yeah, we need to replicate that. That's not what I wanted to do. It's here to here is what we want. Let's go an inch there. 0.5. This also needs to be 0.5. This bugger here needs to be sized at 0.5 as well. Okay, so there's our 3 holes. Let's see if it's going to allow me to do this. Success. Was there ever a doubt in your mind? Should be plenty of doubts in your guys' mind. What am I rambling on about? Dimension. So here to here, that needs to be 1 inch. Now let's draw a construction line right smack down the middle. Shiny. Sure, why the heck not? Now we need to make sure that these two are, well, it looks like it's actually fairly centered already, but we will confirm that. This to here should be 0.25. Oh, it is. And this to here is also 0.25. Oh, it centered itself. I don't trust computers to do that, but it looks like it did it this time. Okay. What is the distance between here and here? 3.5? Perfect. That should be, that's honestly, excuse me, that's about right, because you have just enough to put your hand right in here without bumping into the other lever. I think we're good to go there. We can actually extrude this bad boy. Extrude all of that. Okay. Now we want to, this is where we cut into it. We're going to remove the surface. And now you can see, this is how we get our holes. Oof. Oh, easy now. I'm gonna make you guys even more dizzy. Let's like this. Look at that. This is how we get holes cut. Now we'll... I need to extend our rectangles out some more. So we'll have to go back into our sketch before we extrude that. Take a look again. We need to make these maybe 6.25. I think dingus hit enter once in a while. That actually help. Okay, now let's go ahead and extrude that again, see what it looks like. Remove. And then we'll just go. That's still not enough. It doesn't come down enough. You see how it doesn't come down enough versus in the game? It comes almost all the way down. Yeah, so we need to correct that. Okay, sorry about that humming. I just realized just now that the sim was still running. Ugh. Okay, so 6.8. Look for the unique variable. Well, look at that, it works. Okay. Now, let's see, when we give the old choppy. Let us see how well this looks. Yeah. Great. Extruding. Here and here, and here, and here, and here, and here. Remove. We're going down, down, down. Oh, yeah. Whoa, that goes all the way down. Okay, well, let's not get too excited here. Sure. Let's take a look. There we are. Oh, that looks all right. Yeah, why not? Why the heck not? That's not bad. I'm actually pretty tickled about this. This is so cool. This is really fantastic. So it comes up to here. We'll have, I don't think we'll have a bump up stop against here. We'll have it internally stop. But it is, yeah, honestly, for the lower part where the levers are, that's not bad at all. That's, let's take a look here. That's not bad. Yeah, no, that looks good. It's a little bit long here, and then it drops pretty much straight. Yeah, I think that's good enough. Excellent. Let me go ahead and pause that so there's not any more noise. Okay, so that part is situated. I'll punch the holes for the gauges probably last. Let us get that little crown. Okay, you see the crown on here? Right here. Oh. See the crown right here? Let's go ahead and produce that. So we'll need to make a plane here. And extruding 0 inch for our offset. And then we can go ahead and draw on said plane. You gotta have a plane before you start etching, sketching, whatever. We'll do a 3-point arc again. Now you can see we're gonna go mild or wild. Let's get fairly aggressive. Let's see what that looks like. And then of course you gotta connect those lines up. And okay, and there it is. And then all you gotta do is hit sketch. Oh no, correction. Extrude. We're going this way. I don't know. Was it 5 inches? Okay, that wasn't quite right. But let's take a look at our sketch one. It's 4 inches. All right, very good. Let's go back to extrude 3 and we'll go 4 inches. And enter. Excellent. Now you can see it's all lined up. Perfect. And there we are. This is taking shape. Excellent. Well, I slowly go mad. Let's see. Let's try to make this a shell first. Let's go 0.25 on that thickness. We want it nice and thick here for just for rigidity's sake, because I gotta bolt some holes up here semi-screwed. I don't know how I'm gonna do that yet. Let's put some fillets on here. Nice rounded corners. Oh goodness, that doesn't need to be that aggressive. Geez, slow down, son. 0.5. What does that look like? I don't like the flat tape. Yeah, I don't. Let's try it just for funsies and see what happens. There's a few different flavors we can do here. We can go edge. We can go. Okay, full round doesn't work. Can we do a radius? You can really do some funky shapes with this thing. No, it's not radius. Let's keep it at width. Conic or curvature. Conic fills it out a little bit better. Let's try that. Let's do conic. Okay. It's not terrible, but let's do a fillet on this bad boy. Well, for some reason it doesn't want to do it very well. Can't get it too thick for this part. Can we do width as 0.25? Try and round these numbers up here a little bit. Okay, it does accept 0.25 as a round. Not as sharp as I'd like it to be, but let's accept that for now. Let's see if our 2 side fillets can also do 0.25. Yes, they actually can. Fillet 3. 0.25. And it's screaming at me, fillet 4 doesn't like. Let's see here. That's fillet 3. Oh, oops, I don't want that. Do that. 0.25. Enter. Yes, accept it. Okay, alright. Let's do some fillet out. Can we get a little bit more aggressive for this particular fillet? Oh, yeah, I think we can. Oh. 0.5. Let's do 0.5. There we go. Don't know how these side fillets are going to look like. I honestly do not know. No, I don't want to extrude. Oh, no. Here. 0.5. There we go. I like to do the facade right here as well. I don't know what flavor we can use or not. I'm not digging that. I am not digging that whatsoever. Just for fun, let's round some edges off here. Make it look a little bit half decent, professional-ish. That is way too aggressive, sir. Just back it on down. Distance. No. That is not to my satisfaction. No, I want distance. Just simple curve. Oh. Well, I'm gonna do 1 inch. Yeah, 1 inch is a bit aggressive. 0.75 or 0.75. It's not bad. Not terrible. I wish I can cut this out, which I... This might look awful goofy. That's what people said to me in junior high, but hey, you know what? I don't see me anymore, so... Let's see here... 0.4... Yeah, not a fan. Not a fan. I'm not feeling the fillets here. We can always choose to delete it later. We can delete stuff independently. Like we can delete just this, but if you delete just this, then it affects this. So you kind of have to be a little bit careful. But we're just kind of having a mess about here. We're getting close. Honestly, I'm pretty tickled about this. This is not that bad. Now, if we look at the bottom, it's actually spaced out evenly. Hey, what a novel concept. What a novel idea. Right, let's punch some holes for our gauges. Now let's sketch a construction line. Remember, a construction line is not a permanent line. It just helps get things all centered up. Middle to here. So this is the middle of this quadrant right here, this rectangle, if you will, or whatever you want to call it. I'm not an expert at this, guys. I know just enough to make myself extremely dangerous. Now, this is, of course, all in millimeters. Everything's done in millimeters. I'm doing it in inches because I love my freedom units. We'll just draw 2 circles here right quick. Okay. So we'll go to here. Actually, we'll go to here, and then we'll go to here. And then it's 3.110.236 inches. No, it's 79 millimeters. Thank you. I don't know how accurate we need to be. It looks like it rounds up to the nearest point, but yeah, well, hey, whatever. We can always adjust that later. So then we're gonna have to go split these up evenly. Here's a quick way of finding out where's the middle. So 2.6 is going to be dead center, or it's going to be centered for the most bit. That looks all right. That looks all right. Good enough to me. We'll punch the holes here in a minute. All right, now for the mounting holes. 2.48. Nope, we're not done with the sketch yet. This down here should also be 2.48. That's our mounting holes. Now, for their top 2 holes, they want 2 millimeter holes, which is insanely small, and I don't like that. We're going to be using a number 10 US, which is a 3/16 hole, so I think that's what we're going to do for the top 2. bottom two are actually significantly larger for some bizarre reason. They are 9 millimeters, I believe, 9mm holes. We may have to adjust this just a bit. These are the mounting bolts. They're all squared away. I got them all measured out. Now we just got to do the right diameter here, which I mean, kind of pain in the bahootie. No. Stop. Wait. That's what I want. It's tricky. Tricky. So we're gonna use 0.1. Oh wow, that was close. Booyah. That will fit a number 10 screw. Again, freedom units. Yes. For the win. Oh, come on. Click. Come on. Click. Let's say 0.19er. Yep. Bottom screws they're calling for 9 mils, I believe. 9mm. So it's close to a 3/8. Huh. What size shall we use? Well, it looks like we can use 1/4 inch. They do make 1/4 inch machine screws. I know they do. These are countersunk, which is what we want probably for a flush finish, possibly. Hey folks, this is something you need to just pay attention to. No, it doesn't matter too much. I'm getting way too carried away with this project. Which means it probably won't be done for Oh, they are protruding. These are protruding screws. Huh. Okay, well, they modeled it as protrude, or they protrude out. Huh. Including cockpit. Yeah, that's fine. No, I don't want videos. Heaven forbid, we're not gonna get it. No, we watch a video. High resolution, possibly. Are these protruding or not? I'm always curious. I can't remember. It's been so long since I've been in a Cessna. That's the closest thing I have, which I know sacrilegious. I know. They look like they are protruding a wee little bit. Look. Come on, give me a big picture. Yeah, there we go. I'll be darned. That one is, but these are protruding. They are protruding screws. I'll be darned. I thought they would be countersunk. Okay, well then we don't have to worry about countersinking them. 9mm closest to us would here in America would be 3/8. So 9.525. Oh, it may. Oh, hello. You only do the first two decimals. That's probably why it's 9. I don't know. 0.37. Okay. So, oh, googly moogly. What is this thing? What is that? I don't know what that is. No, I don't want to. And of course, rinse and repeat on the other side. Now we should be able to simply click and drag this component, copy, paste. I really don't want to draw all that out again. You can if you want. I should say that a lot of stuff in AutoCAD I'm quickly realizing. Oh. You can do it in multiple ways for the same thing. Oh, no. Oh, no. No. Oh, don't do that. Yes. And I never use a copy-paste function before. Something like that, perhaps? But why is this freaking scaled 0? Okay, let's just undo it here. Let's just undo. Escape. Zero it out. Try it again. Paste. Let's try that. That still is off, to be honest. No? Is it off? I can stare at this for a second. No, the lines are right in dead center. That is accurate. Okay. Go ahead, hit OK. There are our gauges. Gauge holes. Now for the really fun, easy bit. I'm going to punch holes through them like this. Watch this. Come on. As soon as it loads up at your convenience. Actually, no, we're going to extrude that. Move. We're punching holes, people. Pow. 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 It's like a video game. There we go. Enter. Oh, yeah. That's what I'm talking about. And then we'll worry about... If we have to open up these holes more later, we can always manually drill them out. It's not a big deal. Okay. There we go. Why are you throwing a hissy fit? Oh, I don't care. Go away. Accept that. Excellent. Okay. Now I'll work on these. I'll try to work on smoothing this out here a little bit.
7 months later.
At first I thought this was good, but then I quickly realized this is not quite entirely accurate, so I had to redo it. So this is the version 1, and welcome by the magical art of digital editing, version 2. Well, after picking this project up about 7 months later, this is the new improved version. I really like it. It came out pretty snazzy. It's still subject to revision. I'm waiting on blueprints to see how wide this thing is actually supposed to be, if I can get those numbers or not. I'm waiting for a man to contact me about that. Yes. Anyways, we've made it a little bit more realistic. Right here in this section here, that's where your throttle tensioners are going to be. Those will be those knobs you say "yeah" and "yeah." This one's been converted to turbines, so there's not a third one, but ours will have a third one. But I also made it so we have the DeHavilland Beaver logo flat on our console, so we can put this little strip in here later, which would be right here. We can put it just right below the throttle cutouts right here. So we'll be able to put the logo on there, so it's nice and flat, and should be good to go. And then it's going to be flat down here when we bolt up the bottom center console piece. But it looks pretty good. I'm pretty pleased with it. It looks realistic. I did find that most of the Beavers had a I don't know what you call it, a crown. We want to get really technical, pointing instead of this dome piece, nice and round here. But I did find one picture that did have it more or less round like this. I'm like, okay, so it's kind of realistic enough. Okay, that's fine. But it flows good. I like it. It flows. So this portion of the program, this part of the program, we have to actually put our, we have to make our throttle pots, or our throttle potentiometers, right? We got to make the actual individual levers and hook them up to potentiometers so we can actually use our levers here. So I have a few ideas how we can do this. I'm going to start assembling it, and then hopefully that'll be more or less what the final product will be, hopefully. So we're going to go over here. Let's see, we're going to create a new parts studio. And out of chaos, out of nothing, out of darkness, out of the void, we shall build our console, throttle, potentiometer thingy. Whatever. Okay, let's go ahead and sketch. What plane do we want to sketch on? Okay, we're going to sketch on the top plane. We'll go to center point rectangle. This is the first problem here. Do you want to make it 2 inches? Let's see if we can get away with 1.5 inches. Let's dimension this bad boy on up. 1.5. So as who's losing the news, it's hip to be square. Absolutely. And then we're gonna knock it off. We're going to extrude that. Let's go a depth of 3 inches. Bish bash bosh. Right, so there's basically our mounting block of where the potentiometer will go, the bearings for it perhaps. I'm thinking that may not be wide enough. I don't know yet, so let's just play around with this. Literally sketched on screen. I don't care if this is boring or not. This is not going to be the primary content of this channel, believe it or not. Is after we get done assembling and flying around, that's the main channel, so that'll be the main content of the channel. So right now we're just plinking around and having fun in the sun. Come on. Now I need to split these two up here. I'm thinking about how I'm going to do this for a second. All right, I think what I'm going to do is I'm going to sketch around the middle of this block, and yes, in OnShape, or rather any CAD software, there's about 10,000 ways you can do different things, right? So this is just how I'm gonna try this out here, just to see if this works. Now we need to have the throttle lever pivot on bearings. Are you done? No. Yes, I know. Collect the contract. Mission was collected. Excellent. So what I did is I went out to a McMaster car here. I selected a smaller bearing here. It's a permanently sealed bearing. And I have the dimensions right here. And what's really cool, we go with stuff like McMaster car. I think Granger may do it too, but I know McMaster car does. You can actually select the CAD file, like a two-dimensional PDF, such as here. And that will be, you pull this up and, hey, you got dimensions on your bearings. Standard or metric, it doesn't matter. I'm like, oh, perfect. So now that we have a dimension of the bearings, I don't have the physical bearings yet. I have to order them, waiting for payday, of course. Most of us sim builders don't have a whole lot of cash, it seems, so we just little at a time, slowly start planking away at it. So even though we don't have the physical bearing, we have the dimensions for said bearing, and we can actually start designing it already without actually having the physical part. Isn't that cool? Absolutely. So what we're gonna do here, that never printed out. I wanted this to actually print on my stupid printer. I thought I printed it out. Oh, it's not plugged. My printer's not plugged in. All right, so we got that there, and now we're gonna draw a circle. This will be the middle of the bearing, and then we're going to. This will be the outside diameter. 7/8. So that's 0.875. Perfect. And then that should be good to go there. And then we can extrude this by remove all the way. Boosh. Ah, dang it. You idiot. Well, it's 3 inches just to punch all the way through. And bosh. There we go. So that's where the bearings are going to go. There'll be bearing, one on each side. So let's create a new sketch to split this thing up in two. I'm going to select this line. First of all, that needs to be a solid line. That does not need to be a construction. That needs to be a solid line. Then you need to take this solid line here and extrude that solid line as a surface going the other way, which should be 2 inches or whatever. Select that. So then what you need to do here is you need to go to the split option. Parts, surfaces, or curves to split. Be this chunk of here. Entity to split with would be here. There it goes. So now it's in 2 pieces. So now we can remove just the top piece, and now we can remove just the bottom piece. Okay, so I think this is the top piece. So let's just hide the top piece for a second. Let's work on the bottom piece here. And we want to build a shelf where the bearing is going to sit into, so it doesn't walk around and move all over the place. Very important. So, let's see. How should we do that, Shay? Let's see. Let's do a sketch. Shall we do a sketch? Let's have a sketch. No. It's not going right. Corner piece. Let's dimension this up in case we do get it right. Go 0.125, that's 1/8 of an inch. It's fine. And then what we can do is hit extrude, and we're going to add, but we're going to go the opposite. No, it wants to. Oh, okay. So now it fills it up there, but we want to pull it down because on this. For the tensioner, I may have to have it extruded. I may have to have the shaft on the outside to use the tensioner wheels. Yes, we are actually going to have real tensioner wheels. And who dinged me on Discord? Okay, so then we select on our triangle, go to extrude. We're going to add, switch it around, yeah. We're just going to add to it and just click OK. There's our shelving there. We'll carve that out here in a second. Let's do the reciprocal on the other side. And then we'll go to dimension that bad boy on up. Come on. 0.125, so 1/8 of an inch. Yes. I'm sure I'm driving all of you people who don't live in the U.S. absolutely batty with my freedom units. But hey, it's all good. We're all here having fun, are we not? Just deselect that for goodness sake. Then we're going to go to extrude. Let's go back in and do the extrude button. We're going to hit this one too. Be reciprocal. Okay. Now we need to carve these out. which actually is not that, should not be all that difficult. Looking at the blueprints for the bearing, we know, basically we want to carve this shelving out right here. So therefore the bearing sits on there, its cage is not going anywhere, but still leaves a shaft output. And doing simple maths, this point to this point is going to be about 1/2 inch, right? Because we know the inside diameter of the hole, and we know the hole length of the hole. So we go to 0.375 minus 0.875, and that leaves us with basically the other half of the bearing here. So we should be able to come up with a moon shape about up to 1/2 inch. You guys confused yet? Fantastic, darlings, fantastic. I'll show you, So we're gonna go to here, and on OnShape, you got this cute little circle thing here. It'll tell you when you're exactly squared on, just make a shape, and then we know that it's gonna be 0.5. Actually, let's do something more simple here. This diameter here is going to be 0.5, right? Take a look at this. No, the shaft is a 3/8 diameter. Wow, what was I thinking? So that's 0.375. You donkus right here. Who are these people? 0.375. That's better. And then we're going to go to extrude here. Then we're going to click extrude here. Then we're going to remove. We're going to hit symmetrical, which will cut this portion out too. Or it should, if we go out far enough. If we go out far enough, there, it cuts it out there. Bish bash bosh, enter. Booyah! Not only will the bearing sit in there, but it'll still have a shaft throughput. We may have to open this up a bit more. Let's throw this on OnShape. Let's throw this on OnShape. We're in OnShape. Let's throw this in assembler and see what we got here. I need to add a piece. Hang on, let me import these. Hang on a second. Create new folder. I don't want to create new folder. I just want to add insert. Yeah, that. Whatever. And what's really cool about OnShape is you can actually import. Some people have actually, like checking for bearing part numbers and stuff. You really should do that because believe it or not, people have already made this bearing. So we can actually import it directly. I've got to punch up the part number here. R6 style. So it's -2RS. Now, we're going to hit search and our search function, and there's our bearing. I think I like the sealed one better. I think it represents the seal a little bit better. That's just being that's just being weird. There's our dimensions there. 0.875. You gotta make sure it's the right. That doesn't. Those don't quite look quite right. That looks right. 930 seconds. This could be right. Oh my gosh, she's dinging me now. Hang on. Stupid coworkers and their memes. 3/8 by 7/8 by 930 seconds. This should be it. Let's go ahead. Okay, we can insert our bearing. It didn't do it. Hang on a second. There's our bearing. If we can just get out of here. There's our bearing. See, they already modeled it. Why create that work when they already did it? That's what I like about OnShape on the public side. Is it's really phenomenal. So now we just need to attach this to here. So let's see if we can just do cylindrical mate, and I'm not sure if that would work. Let's just fasten. Kind of hard to see. Somebody got to zoom in. This piece here, that centermost piece here, too, would be the centermost piece here. Oh, hang on a second. It gets a little bit funky, guys. Just hang on. And right about here. Is it close? That was close. Not quite right, though. So let's try that again. Okay, I figured it out. Another reason why I'm making these videos, when I get old and decrepit, but still want to continue making these things, I'm selecting the outermost ring here, is that so I can remember how to do this. Scrap. So click on here, we know, oh no, we're stuck like this. There's a button you hit. You go to flip primary axis and whoosh. There you go. And then of course you can rinse and repeat on the other side. Of course get the other bearing, but you guys get the general idea. So now we got the whole here. Now the tolerances are, there's a little bit of a lip here. This is carved out just enough. We may have to carve this out a little bit more because technically there is no tolerance. The same diameter here is also on here, so we may have to carve this out ever or so slightly more for the fit. May have to do that. May have to carve out this this moon here a little bit more, just to make sure that shaft won't rub up against the block. Maybe give another, I don't know, 1/1000th of an inch, you know, just a very, very small amount carving that out. But that's basically what we're going for. So basically the name of the game here is the shaft will go through here. The lever will actually be inside of here, in which case we could probably make this block a heck of a lot smaller. And then the potentiometer will go on the outside, and the throttle tensioner lever dial thing will go on the other outside here. So we can actually scrunch this up quite a lot, actually. And we can actually figure out how much, because we can actually import this bearing again and put one on the other side that measure between the two. You guys have absolutely no idea what's going on. All right, so let's go ahead and accept that. Go ahead, go to fasten mates again. Again, we want to make sure we're selecting the outsidemost, just so we know that thing will match up. That one matches up perfectly. Okay, we're gonna hit accept. So there we go. So as you can see here, we've got a heck of a lot of distance. Oops, heck of a lot of distance here. So we're gonna get our tape measure, and we can't really. Trying to measure the distance between these two bearings, which I think if I click on there we can. So it looks like center. Oh, oops. I'm sorry, guys. I'm not a professional YouTuber, right? I'm not a professional at this. Let's go to this line and go to this line and measure it. So it's 0.688 is pretty much. Now, obviously, that's line to line there. There you go. Oh, I can highlight it. Look at that. Bang and mush. So that red line's being measured at right now. So we're at 0.68 inches. Now, obviously, you're going to need a little bit for the lever itself. So we can at least cut that in half and go cut this block down about 0.5 inches, perhaps? 0.4 inches? Okay. 0.4 inches. We can do that. We can do that. And at the same time, we can carve out our block just a little bit more, just to make sure this all fits here, just like thousandths of an inch. And that's what's the nice thing about having a resin printer, is it can be that accurate. Okay, so we're back to our block here. It's really easy to tighten this up. Go back to sketch 1, and then this is our width plane here. We're just gonna go back down to. Let's just do 1 inch for now and just see what it looks like. Hit enter. Now see, wow, it just shrunk it all up. Now sometimes you gotta be careful, because sometimes if you get a large enough complex object like this thing and you start drawing stuff up and pushing stuff up in, you can break stuff, and then you gotta redo it a little bit, which isn't a problem. So obviously these are much like a toiga together, much closer now. We can measure that distance. I'm thinking 1/8 of an inch should be good for our throttle lever itself. So that needs to fit in between here and here. And it looks like we're at 0.188 inches. And that's just above 1/4 of an inch. Or just above 1/8 of an inch. That should work out fine. Okay, that'll do. Donkey. I don't know if I'll cut. I mean, we could cut this piece here down towards the bearing a little bit. I don't know if it's necessary. Yeah, I'm not sure yet on that one. I mean, that's gonna be a little bit of resin just doing this block, but we're not there yet as far as mounting stuff. Right now, we're trying to get this thing dialed in. Let's cut this moon shape down, perhaps, and maybe our circle a little bit more, so at least this will have a little bit of breathing room when we squish it all together. In theory, and we're talking thousandths of an inch. We're very small amount. We go back to our sketch 2. This is how we do this. So instead of 0.875, can we do like a 0.8? Come on, hello. So instead of 0.875, we'll go 0.876. And if we go back to the assembler, we may or may not. Yeah, I can see a bit of a difference. There's a little bit more protruding from the bearing. The bearing should sit higher. The bearing should sit higher than the housing, right? Which is here. The bearing should sit a little bit. Yeah, let's carve it out a skosh more, yeah? Maybe I can visualize this a little bit better for you guys. Let's go 0.877. That's 2,000ths of an inch. Yeah, I can't quite visualize that quite well, but you come up to here, this is the bearing surface, and this is the housing surface. As you can tell, they are not even, which is a good thing. We want that hole just ever so slightly bigger. As you can see right here, there's a better visualization. It's just a little bit wider. Not a lot. It's a subtle amount, but I think, honestly, I think that should be good. I think that should be good. We also want to do probably the main housing, maybe cut 1,000ths of an inch off. And again, you can play with these numbers all day long, but in the end, eventually you just have to print the golly gosh darn thing up. So now we need to want to design a shaft, I guess. It'd be pretty easy to do. Let's go ahead and do that. You know what our shaft diameter is for? It's for a 3/8 inch shaft. I'll draw it as a 3/8 inch shaft, and hopefully it fits, because hopefully it's be a nice tight fit.
That's what she said.
All right, so let's start with our building of our shaft here. Input shaft, if you will. So let's start with building our input shaft. So let's go sketch from the right plane here. I'm going to create a circle, and then go to here, and then go to, it says 3/8 diameter, which is 0.375, right? But that's a perfect fit. That's a snug fit. It may or may not fit. So let's just go 3.74 again. We can always change this later. And then if we go to extrude that bad boy, why is it doing that? I don't want thin. I want solid, mates. I want solid. I want a new solid here. Right. I don't know, 1.5 inches? I can't remember. Now, actually, let's do 2 inches. Whatever. All right, there's our shaft. Go back into here. What's the total width of this? Again, if you don't remember, you can either go into your sketch and take a look, or you can get the tape measure up. It's at 1 inch, so 1.5. Let's just do 1.75 on the extrude, just for funsies. Again, you can always change this later, but we're just roughing stuff in right now. Right. This shaft, it's going to be sitting in the assembly right through here. Actually, I could bring that in right now, actually, I think. Okay, there's our shaft. Now, this is going to be a revolute. Oof. Technically, it's going to be a revolute, mate, but I don't know. Oh, we can. Oh, snaps. No. Oh. Well, that's not quite all right, but okay. Alright, well, if it's going to do that, then maybe we can just put the bearings back in there somehow. Oh, now you're going to cooperate, huh? Oh, geez. Okay, well, that's kind of it. Okay, -2 on the Zs. -0.15. There's a better way of doing this, but I'm just trying to rough this in for you guys. So it's 0.35. 0.35. There. Okay, scrub it. Close enough. There we go. Now that's what we're looking for. So now we've got our shaft on here. We need to... there's a couple things we need to do. There's 3 things, obviously. We've got 3 items. We've got the lever itself, which goes in the middle. Right here. And then we need to mount the potentiometer on this side, as well as make a clamp for the throttle tensioner wheel here. Right. What shall we do first? The lever's probably going to be the easiest. Let's do the lever first. Or as we correctly pronounce it here, lever. Let's try to do that first. So let's go back into Part Studio here. Now this bit needs to actually key into an actual lever. I guess I need to make a lever too, eh? I think I do. Let's go ahead and make a lever right now. Let's go ahead and make our lever. This is going to take some finagling and finessing. How wide do you think that? You think that's a 1/2 inch? I don't think it's a 1/2 inch wide. I'm still waiting on the man to come up with my throttle, or with my blueprints. I'm waiting to hear back from him. So right now, let's just go off the pictures. Oh, they are a little bit. They're not exactly square. They actually bevel out a little bit. Okay, interesting. And of course, you want to. Ooh, that has a nice manifold pressure. I like it. It goes up to 50. Okay, I'll make a note of that too. Oh, escape. How do I get out of this freaking? Thank you. So that's one throttle lever quadrant. Let's take a look at this. Yeah, they are a little bit beveled. They are indeed a little bit beveled. Let's take a look at one. Can we get a really zoomed in one look here? Maybe that one, the turbine one. You can see it's beveled out a little bit. Can't really zoom in anymore. It is beveled out a little. It does have a bit of a bevel shape. Okay. Although I'm not sure if the quite suitable because it's a turbine one, but that's an old piston pounder one, obviously. So we can just go off of this. So I'd say they're 1/8 of an inch thick. Okay, that's simple enough. But it's got a bit of a bevel on it. So actually we have to draw this out. So I guess we can't deal with a square. I mean, we can do a square, but you know in your heart it's not gonna be quite right. I had an uncle, unfortunately he passed away not too long ago, and he was telling me, if you're gonna do it right the first time, you know, because when are you gonna have time to do it again? Yeah, it's true. It's true. I mean, the nice thing about 3D CAD work is you can always adjust it, but I want to sketch. We need to sketch on the right plane. Now we will be making this, I will be buying this out of steel. We won't be 3D printing the lever itself. I'll send that out to sendcutsend.com. I just give them my CAD file and then they cut it out. But we still need to 3D AutoCAD it nonetheless. And I really don't have, I guess we can start with a rectangle, I guess. There's multiple ways of doing this, guys. Let me bash this out right quick and see what, bash this out right quick and see what we got. Actually, we can do, no, we can do it together. Let's say this is 0.34 inches, perhaps. 3/4 of an inch. This is, I don't know how tall these sticks are. It's gonna be like 7 inches tall on the stick. So if you look at the cockpit, this goes, because these levers get stuck down in here a fair bit. So I'm honestly thinking 4 inches at least. So 7 inches is a little too exaggerated. Let's do 4 inches just for now. I'm gonna say 5. And then just 0.75 here, but it tapers. And I need to design the taper system. Or design here. It's not a lot. It's a little bevel, or I don't know what it's called. It flares out a little bit. I may have to hand stitch that in. I'm not certain how to do that. Okay, so this is probably going to be a very gradual spline. We're going to start up here, go to here, slowly bevel it out. I know it's got a bit of a round piece. Draw this out to maybe about here, and then hit escape. I said hit escape. That should lock it in. So there's kind of our bevel piece. Let's go ahead and, oops, sorry guys. Let's go ahead and close this bad boy up right quick. Yeah, I think so. So now that we have our slight beveled out here, we want to mirror it right on the other side here. And we don't want to draw this all out again and match it up. You can copy and paste it so it is identical. Pretty easy to do. We'll go line, construction line technically. Find the middle. And let me get rid of this plane here for you. There you go. That's going to be our mirror line. And then we click on mirror, and this is select a mirror line. This is what we want to, this is the halfway mark. So then we go to here, and here. And look at that. There we go. And click OK, and boom. There is our sketch. And I think it's kind of accurate. Let's extrude it just for funsies and see what we get here. Huh? Select the entities to extrude. Let's just do 0.125. That's 1/8 of an inch. 0.125. No, nuts. Come on. No, don't. Oh, I hate it when I hit the thin. Add. New. Solid. Fish brush bullshit. There's a lever. Yes. Not too bad. You can see the tapers down here. Not a lot, but I think it's alright. It's alright. Yeah, nothing wrong with that per se. And it looks quasi-original. If we go over to here again, yeah, say scrub it. Let's call that a winner chicken dinner. So now because of that, we got that. Now we need to put in our shaft. Got on my hat. And I might cut a slit out here. It's just easier to put the knob on, possibly, so that it can flex in a little bit so it pressure holds it. We could actually do that. Go back into sketch 1. Make a new sketch. This will just slightly allow the forks to flex. Like if we, that's kind of hard to describe. If we cut in here a little bit, maybe. And click OK. Now it cuts it in, so therefore you can put a knob on here, and these will tweak in ever so slightly. It's kind of like a pressure fitting. We'll leave a gap like that. I think that should work. And if not, we can always test it out later, or we can just super glue it. I mean, I don't want to super glue it in case I gotta take the potentiometers off. So we can create a notch like there. Now down over here, we need to create an O, if you will, for our shaftway. Now if we look at the assembly, we need to make this custom. Obviously you have a circle. The lever is just going to spin round and round and round, so we need to key this inner shaft. In fact, two of the 3 sides need to be keyed. So let's work on the keyway on the shaft hat. Okay, so we got our circle. Our outer circle is going to be our keyway circle. This will make sense in a bit, guys. Just keep your panties on. We can extrude just one of these circles, actually. We'll go to a line here, create a line here. Escape, hit escape, come on. Stupid old anti-Dell computer. Let's go to extrude. See, there's our shape for our keyway, if you will. And we can't go any wider than, what did I say? 0.1, so it's 0.188, so let's go 175. Now, as you can see, we want it in the middle of the shaft, but this won't do it all. So we gotta start our offset, and we need to, oops, not the wrong one. 0.5. And our depth, starting offset depth, 0.75. That's about right. So there, that will probably do. Let's see what it looks like in the assembler. Okay, see, we're eating into there, so we're not quite there. Okay. So we need to push it out a little bit more. So let's just do 0.85. Let's see what that looks like. It's nice about how, oh, that's not right. That's gone completely the other way. This is nice about having an assembler. Really see what you're doing without printing anything out. 2.8, see what that looks like. There we go. It's almost in the center. That is still not a lot of room, though. That's, dang gum. That's still eating to that a little bit. Oh, there is an air gap. There is an air gap here. Okay, after messing with the numbers, we just got enough of an air gap. That should rotate fine. Technically, this shaft in OnShape is supposed to rotate using the revolute option. I may have to program it offline. It's not that hard per se. I just can't remember how to do it off the top of my head. So that'll come in important because our potentiometer is also keyed, and I need to get that right. Okay, so now that we have a way for our lever to grab onto something and get itself locked in, I need to actually design this piece on the lever itself down here at the bottom of the lever. Oh my goodness. We need to make our little circle that fits this pattern right here. So how we do that is, first of all, we need to remember where our shaft diameter is, which is on sketch 1, 0.374. 374, I should have known that. Go back into our throttle levers. I'm going to do another, actually, we're going to work on the sketch actually right here and draw a circle, dot. And then diameter here. 374. Should we do an exact fit? Nah. No, because this is going to be steel. Going on to plastic. We could probably keep it the same, I guess. Oh, but we want that centered. Oh, please, we want that centered. So we want our concentric command or coincident. I'm sorry. And then let's drag this bad boy. Oh, no. Let's drag this bad boy all the way down here. Something like this. Okay, let's start with that. Okay, there's our O. Lovely bit. Okay, that is. And then we need to make a half. Yeah, and then make another circle. Actually, no. Stop. Construction. No. This goes to here. Deselect that. Then click over there. Then you can click on this. So we gotta remember this. Do we want the top extruded in the bottom? Sure, why the heck not? Remove, enter. There we go. There's our key pattern now. We have it in the assembler now. Looking pretty smashing, bro. Pretty smashing. This is basically what we want. If we delete one of the bearings, you can see when I zoom in how well this is going to work. See the, I'll put it at the center of the screen here. You see how this lever rotates now along with the shaft and how that's keyed? Now that will be able to grab it just fine. You could have eaten into the shaft by removing some material, but that won't work to slip things over, so we need to add material to the shaft, and that's my design, and I guess it'll work, I don't know, we'll see. I did thicken up my lever here a little bit, just because I don't want a whole bunch of wobbling. And if I go to Send Cut Send, for their stainless steel, they offer an 1/8 of an inch and 0.187 of an inch. I can't remember what that is in fractions. Anyways, because there's 1/4 of an inch, and then there's 1/8 of an inch. But picking the middle one here gives it enough guff. They shouldn't have to worry about wobbling too much. And obviously things wear out over time. I'm trying to avoid that best I can. So if we add the bearing view right in here, you can see we just have just a tickle of a room. That lever should float around in here without much fuss. Now, this is too thick up here though. We need this to be thinner. So let's go ahead and swap that out real quick. Oh, you like the colors? I recolored it for you guys. You like that? Yeah, nice and pretty. So two things. We need to thin this back out on the lever on the above part, just above here. Obviously, also, we need to cut into our block a little bit. Now, this rotates only 90 degrees, but we may have to cut it on both sides because you can see the swing over here. It goes, crashes into our bearing holder assembly. So we do need to do that as well. And when we get to the top part of this blue bearing block assembly, we can just mirror it. So we only have to really worry about making one side of the bearing housing. But anyway, so those are the two things. I need to neck this down to make it thinner, just so it looks and feels a lot better. And we also need to cut some slots into this block as well. But we're getting there. So that's basically the rolling theory. And then on the outside will be the tensioner assembly for the our tensioner knobs. And then the potentiometer will be on this side. So we are getting there. So that's basically what we're looking at right now. Pretty cool, huh? Sweet. Let's make a center line. Let's sketch. Let's do some sketches. Let's do a construction line. Out, I think that's what we want. And then center point, we go to here, and then snap it to there. Dimension that up. Point to. Ooh, I was flipping close. And we'll just hit enter. And then we're going to click on these two pieces here. We're going to click extrude, remove, and there we go. Now we're cutting into here. You can make it flush with, quasi-flush with the bearing. Let's see what that looks like. Yes, just accept it. And then we'll just click on assembly and see what it looks like in the assembler. Holy googly moogly, what has going on in here? Oh dear. Yeah, that's, oh, the whole shit, oh, everything moved. It's because I assembled my assembler a bit jankety janked, and I done there broken it. Let me reassemble this again. I got it reassemblated. I just went on to like the revolutes and the fasteners and just ran offsets till I got it right. And now we can see we've got a good 90-degree lever action here again. Action Jackson. Now we can see in the assembler, without 3D printing anything, that it's still not quite right. We see it scrapes down here just a little bit. You can put a chamfer on it or a fillets, but we definitely need to draw that down. So we need an air gap. We need an air gap right over here. So now that we have that, so let's go here. Let's go back to extrude. Let's do 3/4 of an inch. Just say bish bash push and see what it looks like. Please don't mess up again. There it goes. There, that's all right. And what we could do with our lever, or as we properly say here in America, lever, we could put a little bit of fillet on there. Not necessary, but you know, a little bit of professional. You can go here and here, you can do your fillets, and just put a little bit of a fillet on there. Not a lot, but a little. Really? Oh, now you do it. Oh, whatever. Fine. Let's pull this out. We want a lot of strength here, but 0.2. Yeah, that's all right. And then we'll just click on fillet again. Click on there, round two. There we go. A little bit more of a round thingamabobber. We'll go back to assembly. There we go. In fact, 0.75. That's a little aggressive. We like a little bit of strength. So let's just take this extrude. Let's knock that down to say 0.6. Yes? Absolutely, darlings. There we go. Just enough of a gap so now that the swing won't interfere with the block at all. It's 90 degrees. All right, that looks good. Excellent. This is a little bit close in here. You may have to widen that up just a skosh. May have to widen that up a skosh. But this is fine finessing that I can do without you guys watching per se. Now that you've got the general figure, that might require a small bit of tuning. I'm also thinking about it. I might just keep this full solid metal. So Sinka just cut it out and just have it metal all the way down to here. Just use the 1/8 of an inch. I might do that instead. But that's a little bit of fussing about that I can do in the off. You guys, I'm trying to show you guys how to build the biggest chunks and designing and how to use OnShape if you guys want to do this, because OnShape is a free 3D CAD program. So should we do the tensioner first or should we do the potentiometer? I want to do something fun. Let's do the potentiometer.
So what I have over here is our potentiometer. Why does it look so funky? Believe it or not, this is actually out of a car. What I did, I went on to rockauto.com and I typed in Toyota, like a I don't know, 2005, like an 05 Corolla, and then I just typed in TPS sensor, throttle position sensor, and then I was looking at multiple different cars. Now I'm a car nerd here, so I was looking at Toyota, Honda. I decided on the BMW. See how that's got a nice tooth pattern? We can easily replicate that on OnShape. So eventually I wound up with a Toyota, or correction, BMW, but you can do, like if I type in Honda, I looked at the Honda ones, wait for them to come up. Oh, Honda Accord, I guess it don't matter. It don't matter which one. And you just write TPS again. That stands for throttle position sensor. You can use any, oh, that's the actual throttle body. You can use any potentiometer. What I decided to do, this one doesn't have it on this one. Anyways, you guys get the idea. The reason why I went for these is because these are much higher quality for using as a potentiometer. They have to run, 50,000, 100,000 miles without any fuss.
under extreme heat. Obviously more well built and obviously more expensive, but I don't want to keep tearing my apart rig with inexpensive potentiometers. So because I'm an auto nerd, gear wrencher, I decided to find a pattern that looks pretty good that we can replicate our potentiometer in. And then of course, most of the time, if you're like on Rock Auto, you can get the wiring harness. And so I got the wiring harness here, so literally you just snap it into place. And there you go, there's your 3 leads. But all this is a potentiometer. You got a ground, and then you got input and output. And based upon that, when you're twisting this shaft around, you know, the resistance is going to change on these 2 wires. It's pretty simple stuff. It's just a standard potentiometer, only this is for automotive applications, not interior electronics applications. We can also see we've got some very nice mounting holes here and here. Unfortunately, there's no, I don't think there's a 3D CAD software or a 3D CAD rendering of this. I don't think. But all we're going to do is we're going to measure our mounting holes here. Looks like 1.22 inches or whatever. Measure this here with the digital dial calipers. Measure the inside. You can use the backspace of this dial caliper to measure that, your half moon or your 3/4 moons. And the only thing we have to pay attention to is the shape of this crescent inside of here, the keyway, if you will. Now this potentiometer for this application will work because we only need 90 degrees, as you saw in the assembler. So, as we can see here with a car, your butterfly valve in your throttle body only goes 90 degrees. And this also goes only 90 degrees. Excellent. The only catch is it's offset. 90 degrees is not straight with the housing here. It's not straight with the housing here, right? If I fully pull this back, you can see it's not center, but 90 degrees is still 90 degrees, which is over there, which is fine, which is perfect. But we have to worry about this offset, so we have to get this right, which fortunately, this is what the assembler is for. So I'll be taking the measurements here, just slightly off camera, with the digital calipers, and we're going to basically model the receiving end of this onto the bearing block, or bearing housing, if you will. Sweet. You can use other potentiometers too. I'm just choosing something that's far more robust and praying that I don't have to ever open up this throttle quadrant again. Let me take. Okay, so what I decided to do here is, before we go any further, when you're doing something like this, I would strongly suggest you actually get everything wired up to make sure your screwy ideas that are inside your head actually work. So we got Maggie fired up. We have our potentiometers here, or rather our potentiometer, uno, singular, here. I decided to hook it up to 5 volts. And through MobiFlight, which I can show you how to program it later, wire and program it later. This is just for demo purposes. You can, for the Arduino Uno, you can select analog inputs, pins 1, 2, 3, or 5, and those will be your inputs. So you could have up to basically 5 potentiometers or 5 levers or whatever analog inputs for MobiFlight for this board. So it's really simple. 5 volts comes into this red line into here. We have to ground it on the other side, which is the black wire, or earth, as some guys you might say. And then blue is our signal wire. That's the 0 to 5 volts. This volt right here, the 1 through 5 volts, you see on this meter, it's going to the analog pin. It's just to help visualize what's going on. So I stick my screwdriver in here because I don't have the actual 3D printed part yet. We see how as we twist it. This is very precarious. So basically idle is there, and this is what happens in an IRL car. About 1 volt is your idle, and then 5 volts is your max voltage. So as I slowly start cranking it up, you can see the voltage is starting to rise all the way to the top. Okay, 5.16 volts. That's our max throttle. That's if you're shoving the car, you know, pushing the pedal down the floor, and woo, rocking and rolling, as it were. That's what the Arduino needs to see. Fortunately, these car throttle position sensors are meant for 5 volts. 5-volt reference is very, very common even on modern cars, and that's exactly what the Arduino wants to see. And as you can see, when we are turning it, you'll see a light blinking here, hopefully. So I can do this. You see that yellow light right there? That means the board is receiving our analog input, and it is updating it up to MobiFlight, and MobiFlight is adjusting it correctly. Now let's unfreeze the simulator and actually see this in action. Okay, so we're here, Maggie. She's all warmed up, ready to go. We're in beautiful San Diego Park. Mount Hoodoo is right over. If we're facing, if that's the DOT station, then Hoodoo Ski Resort is right over there. We won't be flying right now because we got an airplane to build. So we get into our cockpit here, and there's our throttle quadrant right here. Now, let's test this out again. Put on my headphones because I like listening to it. Okay, here we go. So we're just gonna get in here, do the twist and shake. Perfect. Whoa, easy big girl, no prop strike. Oh, we nosed over. Oh well. I got crash settings off so I can do this stuff. But as you can see, the throttle lever the animation isn't quite so good, but we don't care about that because we're building our own lever. But as you can see on the manifold pressure, it gets a little, it ramps up a little much at the very end further than what I would like it. But the manifold pressure is smooth, which means it's receiving a smooth enough input for us. But yeah, that'll work just fine. That will work just fine. So now that we know we have proven technology here, which I strongly suggest if you guys are doing something like this, I would strongly suggest get a breakout board, get a single board. The Arduino Uno is about 30 bucks. And just start playing with whatever much you want to rig up. So before you start designing your 3D AutoCAD like I am, make sure this thing actually works, you can get it to work, and then you can design your whole system around this device, whatever you want to use. So now that we know this is proven, we can go ahead and model this in, rather the receiving side of this sensor in OnShape. Sorry, Maggie. Oh my. Oh, I'm sorry, Maggie. I'm sorry. You're fine. You're fine. Here. Let me shut you off. I know. You're very cranky. Being very cranky. Let's just shut this off. There we go. That's okay. No prop strikes here. I promise when we get you built properly, we'll behave a lot better. Hey, at least you can do your inspection now underneath your tail wheel. Yep, pre-flight's good. Yep, we're good to go. All right, back to OnShape. Alright, sketch on this plane here, and then we're going to draw a line. Something like this. Right, there's our half moon sheep. And it is, unfortunately, when I bought this thing, I should have tried to find a throttle position sensor that when it's full throttle or zero throttle, everything all lines up 90 degrees, but I'm a masochist, I guess, or whatever. Alright, measurements time. Moon shape is basically 0.1 inches. Basically from here to here, it's basically 0.1 inches. Hey, it wasn't too far off. Okay, that's good. The diameter on this is going to be 0.32. 0.32. Okay. Right. Okay. Extrude. Remove. 0.54. Boom. There you go. There's a receiver for the potentiometer right there. And it should be timed right. If I'm looking at this correctly. Okay, so let's make our clamp. Let's go ahead and go sketch plane top. So we'll get our circles here. Grab a couple circles and then one really big circle, kind of, sort of, quasi thingy. Now we're going to dimension this bad boy on up, so this is going to be our representative of our shaft. And then, we won't get too creative. We'll just try to clamp it out here. We'll make it straight and see what it looks like. Oh, for sure, don't you know there, bud? I'm not sure this is going to work. There we go, using the mirror image thingy program. That's fine. think I can trim it here and here and here and here. Yay! We do have a clamp. Sweet. And I think we can clip away with this. There it is. Been forever and a freaking day since I did this. So there's our clamp. Now, the only question is, I'm printing up our shaft here right now. It's literally printing as we speak, so I can print a few clamps out just in case. We really won't know. Obviously, if the clamp is too large, it won't clamp at all. If it's too tight, then it just won't work. You need to find that Goldilocks zone, and this is the gap right in here. And this is not defined, so actually we can actually define this. So if we need to close that gap, we can go like 0.01 inches, and we can draw it in, as you can see, which that looks visually a little bit better. Okay, so now that we have that, we can click accept, and then this piece here we can extrude 0.5 inches, I guess. Let's just see what that looks like. And there's the beginning of our clamp. And then the adjustment rod will go right through here on the square and hopefully squeeze these two like a toiga. Now we need to make a place where the actual rod goes through. So let us do that now. We're going to sketch on this plane. Okay, so we do need to punch that 1/4 inch hole. Remove all the way through. So our rod can go in there. You know, actually, oh, that's dangerously thin. What? Ooh, that's not good. What I'm envisioning is actually going to work. We're going to extrude this, and we're going to cut away at this symmetric, and we're going to cut it at 0.25. See what that looks like. Remove. Enter. 1/4 inch. Maybe not 1/4 inch. Yeah, scrub it. Let's do 1/4 inch. So this will allow the jam nuts to come into play. Let's see if we can clean some of this up. Now I'm just playing with a little bit of an idea here. And let's just lop that off. Would that work? Yeah, that might work. There we go. Look at that symmetry. It's gonna be 6-sided. Dimension this bad boy on up. Come on. 0.44. No. No. This is going to be extruded. And we're going to remove surface. I'm gonna remove that flipping much though. Calm down. How deep do we want to go? 1/4 inch bolts are not that deep here. 0.25, 1/4 inch, 1/4 by 1/4. 0.25. Enter. And of course that deletes the whole thing, which means this here and this here need to be extruded some more by adding more on there. Oh my goodness. Oh, what the flip. What the flip. Let's do some symmetry as well. Let's get some fat on this. There we go. This is going to be the stupidest, dorkiest flipping clamp anyone has ever seen. Oh crap. Okay. I mean, I think it'll still work. And in here, you know, you could put a chamfer in here, or put a chamfer in here. You can see that, so you can make it a little bit more robust. You know, you don't have to look it quite so ugly, but yeah, that's a shade bit ugly. But hey, won't know until you try it. We gotta risk it for the biscuit. Come on. Okay, let's go here. Going to extrude. Going to remove 0.25 inches worth. Perfect. Right on the wrong side. Brilliant. Who are these people? Right. As we can see here, we've got a very, very primitive prototype done for the throttle quadrant, or namely the throttle lever / friction mechanism for it. So this was design number 1, and immediately after I put it together, I really don't like how these dogs here mesh in with the shaft. It works, and it probably will work, but I really don't like. I would need something a bit more meat for the lever to grab the shaft onto, right? So I was like, okay, well that won't work. So that was version 1. Of course, these shafts also went through a few revisions. I quickly realized that this was not long enough to protrude into the throttle position sensor. So this is basically version 2 here. So we'll take a quick look. You can see that this goes all the way in, right? The original one, version 1, for some reason, yeah, that it just didn't have enough meat to grab right there. That was not going to work. Okay, so this is version 2 that I know of. And you can see I put a heavy duty notch in here. That's to help the lever grab onto the shaft here. Now you can see there's a lot more meat for it to grab, so I don't have to worry about slipping off. Also, when we get this, it's going to be in metal. Send it to a machine shop. They'll get the CNC out. Sendcutsend.com, and they'll laser it out for me. It may fit a little bit differently, so this might have to be adjusted ever so slightly. But worst case scenario, if we worry about slipping off, we can put, you know, JB weld on this side here and here. Now, alternatively, if I was not going to have this made out of metal and just out of plastic, obviously we don't need key. We can make this a one-piece style. But when you reach up for the throttle and you go for throttle up, you got to have the coldness of the metal to make it feel real, right? The plastic just won't do. So this is just basically a mock-up of what we're going to do. But this is basically the design. I think we'll be fine with it. I think it'll stay in. And this is our bearing placeholder. It's got 2 holes in it because technically when I 3D printed it, it's hollow. It's only 2 or 3 millimeters wide. And those are just the drain holes for the resin to drain out to. Someone, fortunately, made the bearings already in 3D CAD on OnShape. It's in the public side of it. So I just simply printed them up, and I'm using them as a placeholder. I need to stop being so cheap and actually go get the bearings, the actual bearings ordered. But this is good for a mock-up, just to show you guys what's going on. Okay, so the bearings will fit in there. Okay, so we're gonna put our lever in here and then kind of squish it together. There we go. You can see there's a little bit of a wobble here. We may have to tighten up our tolerances or make the lever a little bit fatter. This is just small tweaking stuff here, but there we go. So now, as part of the situation, now we get our lower bearing block in here, set it in here, and now we have part of our throttle right here. And you can see right here, it'll focus. So there's our throttle action. And now thanks to this key that we have, now that it's keyed, we can actually put our throttle position sensor on here. Now yes, we still have to make the holes to anchor it to the block. That's fine, that's easy enough. But now, we basically have a 90-degree sweep for our TPS sensor, our throttle position sensor. Quite literally. I do know that this throttle position sensor swings a little bit more than 90 degrees. So if we go for throttle up, we can see it goes way past up and down where it should be. But if we pull this up, it pretty much stops straight. So I'm going to do is I'm going to cut a little bit more of this out in 3D CAD software. Make this come down a little bit lower so you can really pull that lever down to stop the engine. And then when you go up, it'll only top out right, like maybe right about here or so. So I just gotta, put it in the assembler and figure out how exactly I want it keyed. But that is basically the assembly. For the lever bit, obviously we'll make a mirror image of this cap and put on the other side. We have to make the slits here, obviously, for the lever to go through. That's not a big deal. And then and this is the friction clamp. Yeah, this one was way too girthy. Yeah, it doesn't flex at all. You can see here, it doesn't flex too much. A couple of iterations later, and I came up with this. We have the lock nuts on one side, but this one does flex quite a lot more. So that's going to get flipped over to here. Hang on a second. So that's more of the assembly here. Throttle position sensor on one side, lead screws on the other side. That will grip our shaft and allow us to either loosen it up or tighten it up. These exact tolerances, I'm not sure yet. This is not a final build yet until actually I get the lever and get everything assembled. But might probably have to put some oil and grease on here to help this from prematurely wearing out. But that's basically it. Throttle position sensor on this side, tensioner on this side. It'll clamp it down or release it, so we have a active friction knob for our lever, or as we properly say in America, lever. And then of course the main bearing cap going on top of there. That's what we're looking like so far, folks. Not bad, not bad. This should work out nicely. And then of course we'll just rinse and repeat for the mixture and prop levers as well. I'm gonna go ahead and get some more of the design banged out right quick offline. TDS as far as how I want this clocked and all that fun garbage. We will meet you back with a final revision on the assembler. We'll assemble it in AutoCAD, or we'll assemble it in OnShape, which is my CAD software. We'll assemble it, see how this swoops, and see if it's accurate enough with the pictures we see in real life, as well as people flying it around. And if it looks good, we'll go ahead and then design the mount. We'll design the mount together as far as how we're actually going to mount it up into the console. Sweet. So here is our lever. We have our upper cap here installed, and we do a little swing with it. Swing, swing. You can see the actuation. Now you can see that it does not go down all the way, and that's by design. Neither does it go up all the way here. I actually spent a lot of time reviewing videos and realized this is not 90 degrees where this lever needs to be. Let me show you. Alright, so this video comes from AreoplaneToby. That's his username. Full credits to him for this video. Thank you for posting this, Toby, if you ever do find this video. Really helpful to know the throw of the levers. I'll link his channel down below, as well as his video. So we see right here his prop and RPM levers. Although they are up, they're at a slight tilt, but you also have to remember this is a tail dragger. So is this piece here parallel to the ground, or to rather his the floorboards? Probably, but I think there's a few degrees where it doesn't go up all the way. What he's going to do here, though, is he's going to he's going to throw the throttle. He's going to pump the throttle, squirt mixture fuel into the carburetor, and we're going to see him pump it and go full throw. So you can see right here, this lever does not the lever does not go down all the way, right? So you can figure this line right here would be you can see the bottom of this window sill of the door. That's parallel to the floorboards down here. So we can see that there's a 10+ degree angle. It doesn't pull down all the way. Now you can see right here, I have designed that. It's a little bit off. I could probably take off a few degrees, but you can see it doesn't go down all the way. Just like his, you're looking at the baseline here. That's basically where the floorboard is, because this line right here on the windowsill is parallel to the floorboards. You know, we got a bit of a gap. Cool. So now he's going to throw it all the way. So I'm showing you guys what I'm doing. So he's pumping it, pump it, and you can see right here, it pretty much goes up all the way. But is there an angle? Well, if we take a look, if we picture this as the floorboard again. Here, drop your arm there, Toby. Thank you. You can see right here, it's not quite even with the levers here. So these don't go all the way up. I mean, it's close, but it doesn't quite go up. So if you see here, I have modeled that around here, and it's pretty close. However, we do have a slightly bigger problem. So we bring in our throttle console on the assembler, and there's a bit of a problem. The throw on it I am not happy with. We try to have some of the lever exposed here. We pull it all the way back. You see how little it protrudes? It would protrude from the console. But if we swing it up to here, you know, it's a huge length. of here, it's not being thrown right. And there's a reason for that. And I try to manipulate this thing around where it would be the bestest, most ideal. Like right there might work, but honestly, it doesn't feel quite right. You still have a little shaft here, and as you go up, you have a much bigger shaft. Well, deHavilland engineers actually had a fix for that, which is right over here. So it's beneficial if you can get the original blueprints. You can see what in the dilly-dally is going on here. This is the throttle lever. As we can see, the throttle lever is not straight like I have made it. It actually goes down about 6 or 7 inches, and then it hooks back into the, I don't know, idler shaft, I guess you would call it. And then the throttle linkage would hook up, right in this area here. So the way that they curve this allows it to flex, but you can still grab it on for the most bit and not have to worry about the console swallowing up your throttle lever at all. Here's a fun fact as well. And this detail I did not see until, just sitting on a Sunday rainy morning and looking at it properly. This is the throttle lever control. We also have the RPM control, and we have the mixture control levers. They're all different lengths. Not by much, but it's noticeable. Check it. So we're working on the throttle lever. It is 7.6 inches from here to here. Okay, and then that goes all the way down to here, where it mounts up to the airplane. Okay. The other ones is only 6.8 inches on the RPMs, and the mixture control is 6.5 inches in length total, right? There you go. Then you can see it a little bit better. So what we need to do here is we need to design the style of lever. Now, we're not going to get... We'll get accurate as possible. We're not going to do the full bevel here and whatnot. We don't need to get too fancy. The most critical... when we take our mixture lever here, the most critical bit is how long is it from here to here, and my incomplete blueprints do have all 3 of them, so I can have basically an incomplete blueprint set. I don't know if it just lost to time or the particular seller didn't have it. The mixture lever is the only one that has both the length and pretty much the width of the lever itself. We have the length of the lever is in pink. It measures it from here to here. And the width of the lever, which is this line right here, is in fact measured from here. You can go down to here, and then you go over to here. So now we know, based upon those 2 drawings, we can pretty accurately get the throw right. The only catch is when I design the other 2 levers, I'll just substitute the length for each specific lever. That's the RPM lever, the throttle lever. They're all a little bit different. The only thing that really is noteworthy is the throttle lever is almost a full inch longer. Something like that. But since we got blueprints, we can actually print that up. Now let's check Toby's Beaver and see if we can truly see a different length. Okay, so we can see right here, indeed, his throttle lever is a lot taller than his RPM and mixture control. So we know that these blueprints right over here is in fact correct. Or at least this is, they didn't deviate too far from the revisions. I'm not sure how old his planes were. This particular set of drawings is from 1951, so it's pretty early drawings. All right, so thank you very much, Toby. I appreciate that. So it's good we need to redesign our lever here. So let's do that. Does everybody have fun? Is everybody having lots of fun? All right, sketch 1. We're gonna draw on the top plane, remove the plane. Let's see here. How shall we? Let's draw a rectangle here and a circle over here. Seems simple enough. Seems simple enough. Alright, so we got circle and we got square. See what Lucian News says? It is indeed hip to be square. Now get my squares to cooperate. Oh, googly moogly, come on. There you go. There you go, bud.
Remember, we're dealing a Canadian airplane here, so we need to throw in some A's, don't you know?
Oh, for sure. So for this rectangle piece here, it looks like the width is 0.6 inches. So we're gonna go over here. We're gonna go to here and just do 0.6. Right? Perfect. Okay. Hopefully the OnShape has not chosen violence today during this recording sesh.
We really don't have much of a length. It says 0.9 here. It doesn't show how the length right here on the stub end is, but that's quite alright. So let's just put in 1 inch for the length, which is here and here. And we'll go 1 inch. We just got it pretty much on par. Right. Now we need to dimension this bad boy up. We need to draw some construction lines. We need to go to here and go up to here. And then we need another construction line that goes from the middle of this square, which I cannot... well, we can. Hang on a second. There we go. And go over here. And then snap it into place right over here. Perfect. Now we can dimension these bad boys up. So the distance between here and the middle of this... Really? I didn't draw my square right.
Get it in the focus in the camera. So the length is 6.5 inches. Okay, 6.5. This best Bosch. Okay, that's 6.5 inches out of that. And then we can dimension this length out. Is that right? Yes. And that is 3.05 inches. Right there. Distance from there to the square up here, right? So 3.05 inches. Enter. Perfect. One thing I forgot to do is dimension this bad boy up. That's why I was looking so weird. There we go. That looks a bit more proper. It does. Right, so now we've got all that dimensioned up. Now we just basically just need to draw the actual lever. And you know, we could dimension it up, but since we know that we actually do know the radius of the circle. I believe it's 0.85. Now, unfortunately, it doesn't show us exactly what the angle of the dangle is on here, so I'm just going to freehand this. So we'll just dimension this as 3.1. On your computation device. Yeah. We're going to hit enter. Excellent, excellent. And then what we can do, in OnShape, well, a lot of other programs have this as well, but for our OnShape program, we're going to mirror this line right over here. We're going to say, yeah, that's hunky-dory. Now, before we do that, though, I'm going to draw this down just a little bit, just a bit of, just a skosh, a tickle, a touch, like I'm touching the head. Ay, there we go. So there's our 3.1 inch segment here. There's a radius here of 0.75. I think I can draw that here. Let's go to tangent arc, and then we're gonna go to here, and then we're just gonna dimension this. Hopefully this works. And this dimension, I think they said, what is it, 0.75? 0.75 is the radius here. 0.75 rad, that's what that is. If we look on here, yeah, that looks about right. Now this segment here goes on about 1 more inch. All right, so we did that. Now if we do this piece right here, we know we can go out 1 more inch before we put in another radius for that side. So what we'll do is we'll go to the line and we'll just continue on. Oof. There we go. So we snap to this line, okay? Then we're going to dimension this one and this one as 1 inch. Okay. So far, hopefully you guys can start to see it. Now we need to put a radius right over here. And we consult our schematic here. So we notice with this upper bend, it says 1/2 inch radius. Okay? Okay, let's do another tangent arc here. So that radius is 0.5. I'm just trying to get a feel for it here. Right about there. Perfect. So we're going to hit dimension for D, and we'll just do 0.5. Hopefully that won't bollocks it up too much. Excellent. There you go. You can kind of start to see. I know the dimension bit is kind of screwy, but you can see the blue here. We are well on our way. We are smashing it, bruv. Now with these radiuses, this lever is supposed to go down here, but we can kind of see we're kind of got our angle wrong. So let's pull our angle back a little bit. The radius stays the same, but the angle stays the same, but we're repositioning it so the center of this lever can go down to the center of this right over here. So now if we draw a line here, you can kind of see, yeah, we got a rough shape. We got a rough shape. In fact, actually, we can snap it to here, and then we'll do another line, and we'll snap it to here just for funsies, and let's see what it looks like. There we go. Now, I'm not going to go full tard here and actually do this little piece that kicks out here and here. We don't need to get that fancy. The biggest thing for the pivoting and for scaling is our length and our width dimension from this point to this point. That will make sure that everything actuates correctly. Those are the two biggest factors. That's not bad. It's not bad. It's all right. It's all right for a replica. And then all I need to do down here is put in my keyway, and this will be our custom keyway, which is on sketch 1 here. So basically, we're just going to copy and paste this back over here. So let me just do that right quick. Who's with me? Anybody still watching this? I highly doubt it. This is not my main content. This is just to show how I'm doing stuff when I get old and decrepit and design another flight sim rig if I have time in my life to do another one. I'll kind of know what I'm doing. Ish. Okay, I think we're ready for extracting. This is the part we actually make something cool out of this thing. So, oh, no, we need that. We need that keyway. That does not need to be extracted. There's our keyway. Oh my gosh, we don't need it that deep. 1/8 of an inch. There we go. So that's under the extraction process. Things look groovy here, baby. We do need to shear that off, which we'll have to do that in stage 2. That's fine. But honestly, I think that's just fine. So if we go into the other part studio right quick, we're just going to take a look. The shape looks to be the same. It should work. Let's just click accept. Okay. And now we need to delete this here. Let's just go into here. We'll just go to extrude, and then we'll just go to remove. Make sure, yeah. We don't want it to go down all the way, so we're just going to extrude this bit, hit enter, boost bash push. That cleans that keyway up nicely. And there we go. Woohoo! We have our lever. Now let's throw it into the assembler and see what we got. And we're just going to go plunk. Thank you. And we'll accept that. And we'll rotate that 90 degrees. And then we're going to put our lever in here. We'll use the keyway to fasten it. So this keyway here. Oh. So we're going to use a fasten mate. See right here, the blue line is pointing down. Okay, so the other line's got a line on the upside, which will be here. Push, pass, push. Enter. Look at that. Look at that. Not bad for a stupid redneck hillbilly out in the backwoods of the Northwest. Hey, love it, peoples. Love it. Now, will this automatically rotate or not? Oh. Okay, it will. It will. Now you can see right here, I put the lever, or you guys incorrectly pronounce it, lever. I put it on backwards here. So what we need to do is we need to select our fasten mates. We need to go to offset and rotate about the z-axis 180 degrees. We need to flip it over and go. There you go. That's like it. That should be somewhat good. In fact, I'm realizing my console's may not be quite big enough. I might need to holler out a little bit more, but there we go. So, now unfortunately, I don't have the full schematics for this thing. I don't know where the center axis is supposed to be in this console. I built this console pretty accurately, judging through the thumbnails and whatnot. It's close enough for us. However, thanks to people like Toby here, we have the beautiful view on how it's supposed to look like. We can see 4 of his fingers on the throttle lever, so we know how that far is supposed to protrude out. We can see that it's a little bit stubbier on this side. Okay, that's fine. So thanks to people like him, we actually have a fairly clear picture, so we can just eyeball it. So that knuckle, I'm 99% sure that's supposed to be buried. That knuckle does not show up in the video whatsoever. There's the full sweep. Yeah, it just smashes into there a little too much. So that's probably full sweep right there. Full sweep up, and then full sweep back. That's not bad. I think we just got it, folks. I think we just got me monkeying around. Now, as you can see right here, the length of this shaft here, it pretty much stays the same length through the entire throw, forward and back, or aft, if you will. We can see that lever pretty much stays the same. It doesn't get swallowed up by the console here. This is flipping fantastic. We can see it sticks out of here. I haven't put it in here because I just had to visualize it lining up. Where am I going to mount the holes? And obviously, this throttle console, I'm going to have to make it a little deeper. I'm going to have to extract a bit more of this. But, I'm so excited. That is probably about as correct as we are going to get. That is banging. And we do have one more slight problem, but if we look at this, it's resting here. If we take a look at Toby's video, we can see that he has his hand off here, and it's resting right about there. So, yeah, honestly, that's about idle. That's where it should be. Now, the next sort of little problem, which is a relatively easy fix, let's put our upper cap bearing piece back on. Whatever you want to call it. So we can see right here that it's not designed quite right? If we go full throttle, it's going to actually mash up and go right here. So I need to make these cutouts a little bit different, which is not a big problem. Also with this shaft here, since we remodel it, we have to make sure that it's not binding up here anywhere. I don't think it is. Now, what we're going to have to do, this was the original stop I made for the original lever, but that's not going to do at all. I need to bring it up to here so it rests up against the lever here as a bump stop. I don't want to rely on the throttle position sensor banging up against it per se. I'd like to have a mechanical stop before the potentiometer or the throttle position sensor limits us. I'd rather have a hard stop instead of using the throttle position sensor as a hard stop. And also, obviously, when we go full throttle, now that we have this in the assembler, which is such a blessing to have, we need to find our new stop here. So this is going to require a bit of engineering here. I'm not gonna lie. It won't be that bad, honestly. You can even see our throttle position sensor move. Look at that. This was nice about OnShape having an assembler. You just make all your pieces, then throw in the assembler, learn how to use all these pieces, and you can see how everything interacts, or sometimes don't interact. Like here, you can obviously see your design there, bud, needs to be, it's not right there, bud. You need to fix that. Right, so now what we need to do is we need to create the mounting holes for our throttle position sensor assembly, I guess you want to call it. We do know the dimensions of these holes that I have drawn off the previous sketch for this, but since we're in here, we got to look right quick. Do we like what we see? The lever is pretty much in center. The throw of it is, oh yes, the lever is definitely levering. We like that. So let's go ahead and take the measurements. Now, fortunately, with OnShape and its assembler, you can actually, between two different objects, actually measure stuff. So we know that our shell is 1/4 of an inch thick. So I'll have to factor that in. We need to measure from here to here. We know this block here is 1 inch. So let's get the tape measure out, or it looks like 1.5 inches. Excuse me, it is making a liar out of me. So we click on our measurements, and we're going to click on the corner here, And we're just going to pretty much draw a straight-ish line over here. And it looks like it is 1.135 inches. Write that down. 1.53 inches. Right. Excellent. Thank you. And then this block right here, it might be 1 inch. Tell you what we'll do. We'll just go into the block and actually see. So this is the lower block. Bearing holder lower. How low can we go? And we're going to select this measurement here. Okay, that's 1 inch. Perfect. So based upon those measurements, we can actually start drawing this out now. So this is our throttle console in the part builder. Actually, hold on a second. I need to make sure we're going to doing the mixture one first. So that would be over here. I just want to do lines here, please. I just want to do some lines. So we're going to snap this to 90-degree angle here, 90-degree angle here. And I forgot to make that into a construction line. That's fine. Okay, excellent, excellent. So that's the shell. So now we know where to start counting. So we know that we'll have to have one gap here and another gap here. Okay. And this is the tensioner, so it's going to be up in this corner area. We know that this value is 1.135, right? We just pulled that off. And then this value here is going to be 1 inch in toto. And this is the very edge of the block. Now we just need to know how deep to go down. We're going down, down, down. So if we look at the base of the block, I've already have the holes pre-punched. Countersunk, about 1/2 inch, I think it's about 1/2 inch. I don't remember. Whatever. We're going to go to sketch 12. Okay, here's our other dimensions. So now the center of the block is 1.375 inches. So 1.375 inches to middle of the block. Okay, so now then we need to make another line. This is basically where the block is going to be. And we said that it is 1.375. Okay. That should be the middle of the block. And basically, that's basically our block right there. So 1.375 is going to be the middle of that block. So we need to draw a rectangle, blah, 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 1.5 by 0.6. So we know that's 0.6. And here, this is 1.5. Boom. Now, mind you, we're not recreating the block. We're recreating the holes that go into said block, right? I think that's actually done. I think we've done it. I think that's it. Now, what we're going to do here is we're going to add a countersink bore in here. So we click on these 4 dots. That basically represents the center of the center of the mounting holes. And now what we simply do is go up to here and go to holes. And it's preparing hashtag feature name. Oh goodness. Wow, we really got to think about it, don't we? It's not that hard. It's just 4 holes using very small screws. Okay, we're gonna have to wait a minute apparently. Okay, we're gonna try this again. This is being poo-poo head. Okay, so there we have it. I am using these as an insert size for the brass inserts, the heat sunk inserts. This was done before. What I did is went on McMaster Car. I figured out it's an 82 degrees for the countersink angle for the head. And I just said, just go 1/2 inch down. I actually just punched it all the way through. That's fine. And then the width of the head, I again got on McMaster Car. It's in the specs. And there we go. So we should have 4 holes that line up, hopefully. So now that we see we've got holes here, kind of see them. I got holes in here, so in theory this should match up with here. So let's use Fasten Mate. Use that down there, and then this should click up here. click. And then we hit accept, and in theory, those holes should line up now. Let's take a look. They do. Oh, wow. Wow, we got it right the first time. Huh, I'll be darned. Isn't that cool or what? Perfect. Now, all I have to do is rinse and repeat this 2 more times, build 2 more levers. We got the mixture lever, and looking at it, the prop lever is a little bit longer, and then the throttle lever is just a little bit longer yet. So let me go ahead and model those in, and I'll show you guys what I got. Worst case scenario, all I'm thinking, oh, no, I see a gap right here, which means this block will not be touching here, which actually that will work out nicely. And, yeah, looks great to me. Excellent, excellent. All right. All I'm going to do is just go back in here and just basically go back into the sketch and just do this 2 more times. You just basically select it, and then you go, you can flip it the other way. You can say you want it 2 more times, so you can hit it twice, and then you just spread them out to wherever you need to be, like that. You guys can quasi-see that. The 2 triangles there. It's just a bit more faffing about. So let me go ahead and bash this out. I'll get the other 2 levers drawn, and we're pretty much going to see the end result here. I would like to note right quick for you guys, if you ever wanted to copy stuff in the assembler, it's really easy. All you got to do is select what you want to copy. Then you literally go copy these 3 items, and you go paste these 3 items. Boom, there's another block. Paste. Boom, there's another block. Once you learn your CAD software, you should be able to start moving a lot faster like this. I do have a prop lever now and a throttle lever now, so just give me 2 seconds. I'll get that fastened, and we'll see what that looks like. And through the magical art of jump cuts, we have our 3 levers. Yes, all pretty much all centered. This is what the back here looks like. I'll have to measure the gap between the potentiometer and our friction holder mechanism. They might collide. I don't know yet. It's going to be awfully close, so I'm going to have to hum about that. Maybe print some of this off and just gauge it, just to see if it's going to fit. You can only do so many measurements before you have to start printing it off and see how close your tolerances really are. So do you remember when the 3 levers, I said they looked a little bit, they were just a little bit different? This is actually true. The RPM control lever is 6.8 inches long. The throttle lever is 7.6 inches long, and the mixture control lever is 6.5 inches long. And what you get is the throttle being the longest here, and then the next longest would be your prop control, or your RPM, right? Because Beaver has a constant prop. And the last one is your mixture control, and that's the shortest one. I don't know if they intentionally, the engineers thought that, saying you can go by feel, maybe in a hurry. You might be able to figure which one is which. I don't know. But the throw of them looks pretty good. There's our throw for the a prop. Looks pretty good to me. Of course, you guys already seen the mixture. And for the big bad boy, be the throttle. And looks, for replicating purposes, I think that's going to be about as close as I'm going to be able to, this redneck's going to be able to get. But it is pretty much true to form. We do have 3 different lengths of levers, and we can confirm that with real pictures. See how here, picture 1, the throttle on this particular Beaver is in the middle here. We can see that's the longest one. The mixture control is the next longest one, and it looks like the prop control might be a little bit shorter, but these knobs are not correct, I guess, for my blueprints. Perhaps a clearer picture will be this one. This is the way that my blueprint is set up, so this is the longer one. Throttle is the longest. Here, for the prop, you'll see it's fairly long, and then we get this cute little stubby guy down here. So as we can see, 3 different lengths. That is actually correct. Fantastic. So going over to the live cam here, I just printed up a mock-up version of the throttle console, and quickly realized, yeah, definitely there's not enough room as the look like in the assembler. There's enough room where we think we can make our tensioner coupler work just fine, but as you can see, it's just way too close to here, and I really don't want to move it out because this is the correct size. I have the blueprints. I got this throttle console pretty much dialed in as far as the dimensions, and this won't do at all. As you can see, there's our mounting holes that go on the back of the block here, and when I square it up nice and evenly, it doesn't work. Plus, I'd like to be able to service this at some point, possibly, if I have to swap this out, and it's just too cumbersome. So, what we're going to have to do is re-engineer this a little bit. Now, I don't want to change the geometry of moving this lever back, because then the lever is going to be not the correct, it won't have the correct throw on it, and I just have to re-engineer it all over again. I really don't want to do that. So what we're going to do is we're going to, on OnShape, I'm going to put the potentiometer from here. We're going to mount it back here, flip it, like this, and then we're going to make a couple of gears. A gear here that will mesh in with the gear here, mounted to this block, and therefore we can still have our potentiometer. We're just throwing it in the back side of our throttle bearing assembly, and that should work just fine. So let's go ahead and model what kind of craziness I have in my head.
All right, and then we're going to draw on this plane here. Dimension this up. Let's see here, 1/4 of an inch. That should be fine. That should be plenty enough for it to grab. Then we're going to extrude this by, say, 1 inch, shortly. So there's our bracket. That's the that's going to go. That the TPS is going to be held on to, or potentiometer, whichever one you like. There's our bracket. This will be where the potentiometer will attach to. Close enough. Perfect. And then those holes simply get removed. Remove surface, thank you. So there is our mounting bracket. Next thing you do is make the hole for the shaft, I guess. I forgot to do that. Show. That will be here somewhere. And this dimension is, we'll do 0.45. And this is just a through hole for the gear to go into. Accept that, and then we're going to extrude, and of course we'll go here as well. Okay, now you guys can see it. There we go. So that's where it's going to mount, right? Right. So we're getting there. Another thing I need to replicate is this little groove in here for the potentiometer. This is how it's designed. So I got to dial this in right quick. And that will solidify that. Okay. Alright, I'm liking it.
And in case you guys didn't know what that little ring groove is, it's just the design of the throttle position sensor. Right here, there's a bit of a groove. Feeling groovy, baby. And so I gotta cut in a little bit of that piece into the bearing housing just so it sits flush with our mounting holes with the housing itself. So that's all that it is. Easy squeezy, lemon peasy.
Right, so dumb like I am, I put the ringlet for the TPS sensor on the wrong side. It belongs over here. You dumb twit. Anyways, whatever. Moving on, let's create the gear for the throttle lever side. Trust me, this will all make sense at some point. Now, OnShape does have a tool up here called Spur Gear. You really can make a spur gear, just click and hey, there it is. Obviously, we have to define exactly what we're doing, but it sets the. It really makes it a lot easier to just throw in something here and modify it instead of having to draw this out all manually. Which you can do, but it's way too time intensive. A fun fact: when I started learning how to do OnShape, I was still am following a guy called Teaching Tech. I can't remember his first name off the top of my head. And he was showing me, today in this episode, we're going to make spuggies. I'm like, what the freaking heck is a spurgy? Obviously, he's got an Australian accent. It's like, is this just a nickname for spur gears?
No, what are you saying? He's saying spur gears, but it's not the Australian accent of spurgy. I'm gonna make some spur gears here, you know? And I can't do an Australian accent all that well. So it took me a hot minute to realize he's saying spur gears. It's just in a heavier Australian accent. I'm like, oh, okay. So that's what that is. So anyways, he taught me a lot, and I'll link his channel down below. No shade him whatsoever. He is his tutorials really helped me a lot to create a lot of stuff, and he does do a lot of the basic stuff. So you guys are genuinely curious on OnShape and how to make stuff. So if you guys are curious, I'll link his channel down below so you can watch all that stuff. I do highly recommend it. So we're gonna make some spur gears here. Depth. So the first bit here, you can make a depth. So you can make it 0.125. That's fine. You can make it as thin or as fat as you want. For us, we'll do 1/4 inch gear, and we can always throw this into the assembler, and we can see how good it looks at that point and justify it from there. Number of teeth. Let's do the pitch diameter of 1 inch. Let's make a 1 inch gear. Let me take the planes off so you guys can actually see this easier. There we go. And I lost my sketch. Lovely. 0.25 for the depth is fine. Pinch diameter is 1 inch, and then you want it's got to be 30 teeth, 40 teeth. It really won't matter. If you put in more teeth, then it'll automatically change the pitch diameter, so you need to redo that again. Not a big deal. Yeah. Wow, is that depth really point? That's a really fat gear. Yeah. Well, we can do 0.2, I guess. It's not load bearing or anything, so that's fine. 1 inch pressure angle, so you can adjust all the pitch and stuff like that. We really don't have to get into that a lot, but that's all right. That's all right. 40 gears. I should mesh it nicely, I should think. And now what we can do, now that we've created our gear, we need to make our keyway. So we're going to go to sketch on our gear now. Draw a circle, circle, dot, dot. Now you got your cootie shot. Booyah! Let's try center point here. So we'll go center. Where's on the other side? Point on the other side? I'll point on the other side? No? Yes? Fine, whatever. And our dimensions. Oh, I gotta grab those. I need to take a look at my throttle shaft. It's a circle is 0.0 or 0.3 inches. Oh, by the way, with this, you can actually measure the diameter, which I've failed to show you guys. You can go from diameter to here up to here to here. And you can see it's about 21.79 inches. So I think, honestly, I'm just going to keep it at 20 inches just to keep it simple. And that's how you can measure this angle of the dangle right here. Actually, probably going to make it a little bit bigger than that because we need to have a little bit of a tolerance. 0.30. I'll give it 10,000ths of an inch clearance. That's probably way more than generous, but that allows it to slip over the shaft without smashing it and having a tight press fit on there per se. This doesn't matter too much. It just has to fit on the shaft. So we're just going to click OK, and then we're going to hit this. Oh shoot. I also need to measure what the distance is from here to here, because that's still moving. See if it's not in blue. If it's in blue, naughty. Let's dimension center of circle to the shaft itself. 0.085. Okay, we can do that. Distance from here to here is 0.085. Enter. Perfect. Now that we know that keyway will be able to fit nicely, should, in theory. Oh, it's on this side. I'm drawing on this side. Whatever. Now this is all backwards, whatever. And then this, we're going to extrude this, and we're just going to simply go remove, check mark, be special bullshit. There's our gear. And believe it or not, we actually put that in our assembler and take a look and see what we got. Okay, so we go to gear, we'll go to blink, and we'll hit OK. Now look big in there, but obviously in here it's actually quite small. The gear, it's so cute, isn't it? We may have to modify this, but for now, let's go ahead and put this on our shaft here. Let me get rid of our throttle console so it's a little bit more cleaner here. And then what we're going to do here is we're gonna have some fascinating facets. Let's try, in the middle here? Okay, we can try that. And I want you to fasten onto here, Okay, well, we kind of have the right concept. Now we just need to flip the axis over and hit solve, or hit the check mark. Hey, look at that. And now in theory, if I move my lever, or you guys improperly say in other countries, lever, the gear moves. See that a little bit better. There we go. Okay, so that's our working concept at least. That 1-inch gear. This gear is going to be way too flippin' small though. Because the throttle shaft is clear over here. And, yeah, that's not going to do it all. That's not going to reach over here. But you guys get the general idea. So all I'm going to do is rinse and repeat for the throttle position sensor. And we'll get these in the assembler and we'll see what kind of adjusting we're going to need. But that's basically the gist of the idea. The next bit is just me having a good mess about and making sure these are the right sizes. 2 of them now. I don't have a shaft going through here, but that doesn't really matter for all purposes. We can see that we have a bit of overlapping. I decided with this gear I'd make it 2 inches because the 2 inches, this is mostly 2 inches. It should mesh up just fine. However, if we take a look at here, we notice that our gears are kind of overlapping each other, so we do need to space them out just a bit. These are both 2-inch gears, so 2 inches plus 2 inches is 4 inches divided by 2. They need to be exactly 2 inches apart. So all we have to do here is go into our sketch here. And we will need to, first of all, let's see, create a midpoint here. Then we need a distance. We need to measure between the center of the gear and the center of the gear, and that needs to be 2 inches, right? Show something like that. So you can see it's 1.94 inches. So it needs to be 2 inches. And we can see we broke it, which is fine because that other dimension is over here. So we delete that dimension, and now you can see it all shifted over here. So we're going to hit accept, and now when we go into our assembly, we should watch it move over. Bink, like that. Perfect. Now we know that our pitch diameter spacing is correct, so these should mesh up just fine. I can probably animate this for you guys, it's not a big deal, but as you can see with our lever here, that works for that. So now what I need to do is basically get this animated and see how these gears interact. So to get them to animate with each other, if you really want to get technical to make sure your build's correct, we're going to go to gear relation, select our mates, which is going to be Revolute 2 for this gear, and which it might be this gear. Let's see, I gotta figure out which Revolute. It might be Revolute number 1. I'm not see here. I think it's this guy has the relations with each other. Hey, look at that, they snap to each other. And you can see they're still off, so we can fix that. But now those two are synced up. Those two Revolutes are synced up. Just right quick, if we can see it, we can kind of start to see they're starting to interact with each other. Now, obviously, both gears are going in the same direction. Obviously, that's not going to work, and we're not quite synced up. So now we got to fix that issue. And I should note that these are both 2-inch gears, so the ratio is 1-to-1 ratio. If this was like a 1-inch and this was a 2-inch gear, then it'd be like a 1-to-2 ratio, and you plug that number in. Yeah. So in the gear 1, to reverse direction, you click this button here, and now we can see that it's animated correctly. As we push the lever forward, the other gear reverses, right? That is correct. The only problem here is, the last problem here we need to basically solve is getting these two gears to sync up to each other, right? So let's do that now. I think this one requires some math. So to go to our Revolute 2 here, I think either one of these mate connectors should work. We click on there, and the rotation angle, there are formulas for doing this. I just like to do it on the fly. Let's do 4.5 degrees of rotation. You can see our gear almost snapped into place. Come on, OnShape. And OnShape froze. Come on. Thank you. Let's zoom in here a little bit. There are formulas for doing this, but those formulas make my brain hurt. Let's go 4.8, 4.75. 4.7. A little bit more. That's about banging mush. Look at that. Not bad. It's not bad. And we're just going to click accept. Now we have perfectly meshed gears. If we rip tight this, look at that. Now you guys can see what the dealio is. Without even printing anything up, so you guys don't have to have a 3D printer right away to do stuff like this. If you want to plan and engineer stuff like this, you can do this on OnShape and get it all figured out. Now, obviously, when you get the printer, you realize the tolerances are going to be a little bit loose or a little bit too taut, like a twiga. You're going to have to modify it ever so slightly. But you can assemble all of this in here. How fun is that? And, engineer something without really spending a penny. You just need the electricity to boot your computer up and get on to OnShape. So, internet cost and, electricity, that's all. You don't have to have a 3D printer yet if you want to build something as awesome as this. But yeah, so that works great. Now, there's one ever so slight problem that we will have to address, and that's the backlash, or the slack between the two teeth. These teeth are it's going to be awfully tight. They're going to be scraping each other a little bit because there's no offset. So we need to shrink one of these sides of these teeth down, or basically create backlash. There's a little bit of slop in there. Not a lot, but just enough slop that these two gears won't bind on each other. And that's fairly easy to do. And there are two ways of doing this. And we'll do this both in our sketches. What you can do is either get into your main sketch where you originally set up your holes are going to be, and we can actually move this out a little bit. So if we, instead of 2 inches, we could go 2.01, that's 0.10 of an inch. See how much that's scooted over? That's one possibility way of doing it, but I'd honestly, there's actually a much better gear in case you don't want to mess with your geometry in your sketch. You can actually do that in either one of your gears. Let's use the throttle position sensor gear. So you go back to the tool in our sketch for our gear where we originally made it. Profile offsets, backlash. Boom, there it is right there. So 10,000ths of an inch, so 100,000. So that's 10,000ths of an inch. Now, watch carefully. When I hit enter, these gears are going to shrink ever so slightly. Watch. Boom. You see that? I'll do more of an exaggeration here. I'll go maybe like half an inch. Well, that makes it disappear. Let's do 4,000ths. You start to see them come back. 0.2 inches. That's 200,000ths of an inch. So 0.05. I guess that's what I should have done. Now see how pointy they are? Like they're worn out. We just want 10,000ths. 10,000ths is should more than be enough. Like that. And that's how you create backlash. I'll have to assemble this thing. I may have to print this out a few times to see what the resin tolerance is going to be on here. But now that we added 10,000ths backlash on there, whew, we are just about done with this monstrosity. Zoom in here, we see there's itty bitty tiny gaps. There's itty bitty tiny gaps. Well, we're only going to do that on one gear. That should be more than enough to compensate for the other gear not having standard size. So yeah, excellent. So then we'll just yeah, we're going to do. There we go. And if we add the rest of the ensemble here, now you can see why I chose gears, because we barely have enough room. So this will transmit the torque from our actual rod of power, and it'll actually transmit it down to here. As we can see, we don't have a lot of clearance, but we have just enough clearance that gear will not touch. So what I'll probably end up doing between the actual gear and the mating housing for the throttle position sensor and the lower bearing block in total, I'll probably put a nylon washer between here, just so things don't rub too hard, because obviously this is bolted right up against here. It's going to rub and it's not going to work. Things are going to jam up. So I'll also have to cut a hole in my drawing and attach a put a bolt hole in there, and then we're going to attach a washer just to keep the gear from walking off if it's not an exact press fit.
just for peace of mind. It'd be a lot cleaner, and I know that the gear is not going to walk off. But that's basically what we're looking at, folks. And yeah, just rinse and repeat, and we can see we got enough room on our adjuster wheel for our friction tensioner. It clears that, but we don't have to change the geometry at all. This is banging. I really do like this. This is coming together nicely. You guys, how I've drilled holes, so I'm not gonna rinse and repeat on that. I'll just make that off right quick. So really, the last flipping bit that we have to do, because we got our mounting holes down here, is the knobs. Gonna be some knobs. You guys want to do some knobs? We gotta put some knobs on these bad boys. Okay, so we're gonna do the prop knob first, just because funsies. Got a big squacking out. I'm gonna put this probably, let's do 1.5 inches. How wide should I set this? Well, unfortunately I don't have the blueprints for the knob itself. However, I was on eBay and someone actually had a tape measure measuring one. Now, full disclosure, this is actually for a Cessna 310, not a DeHavilland Beaver. So I don't think we've got the curve we have in there, but judging by that and another picture from another YouTuber I found, 1.5 inches, that's actually not, that's pretty dang close in my opinion. The shaft is 0.6 inches. So looking at this, one can reasonably suspect that could be 1.5 inches. We can put it into the assembler later, and we can determine if it looks quite right or not, judging by other photos. It would be fun to have the blueprints, but unfortunately, you just can't have it all. These planes are very old, and some of these blueprints are simply lost to time. So you kind of just have to roll with the punches. So we're going to try fabbing this up without blueprints and see how well we get on. Probably going to be referencing this one the most. Okay, so we're going to do a midpoint line. And then we'll dimension this up. We'll do 1.5 at the bottom here. Just pulling that out of my rear end. And then we're going to do a standard line that goes from here. Oh, wow. We have chosen violence. Excellent. All right. And then it basically goes up here-ish. And then another line by here to here-ish. I suppose I need to make another plane. Actually, let's make this independent of this. We'll just go. Yeah. All right. Okay. There's our very, very rough shape. That's 1. Let's just make this 1.5 down here. And up here. Let's see here. So I think I'm going to do is I'm going to create a construction line, probably about up to this level, and then a circle that will cut into here just enough. Let's do 1.5 inch circles, and we'll do the same here. 1.5. Our circles are good. Now, obviously, I have to space them up correctly, but now hopefully you can see the shape, potential shape of the knob. 1.5 is too big. Let's do 1.3. Okay, and we can bring this line down just a little bit to cut into it. So something like that. Still a little aggressive. Let's pump it down to 1.2 inches and see what that looks like. This might require a lot of messing about, but oh, that's getting closer. That's getting closer. I'm just, more or less, I'm just freehanding this, guys. But that's, yeah, possibly. Maybe 1.1 and lower just a little bit more. What will that do? Bring it down into here. What does that look like? Yeah? Yeah? You guys digging this? You won't accept it. Alright, let's just accept it and we're just going to extrude it. Uh-oh. Uh-oh. Please.
Please, OnShape, don't be stalling out. Extrude this, and we're gonna go 0.5 inches. Let's go. I think it's a half an inch wide, to be honest with you. Boosh. Now we need to put some fillets on here. Please, fillets here, fillet here, and we're gonna go to fillet here, and then I don't know. Is that too wide? Are those circles too big? I don't know. I'm being a perfectionist again. Gosh dang it all. Well, let's put some fillets on here for funsies and just see. I don't know if that's gonna work. No, that's not gonna. Let's see here. There's a there. Actually, can we put a fillet on top there? No, you're gonna scream and cuss at me. All right, shut up. So let's go to here. We can go to we can do this and this, and just barely find the meeting point. Something like that. We can also do it for here, and here, and here. We can do all of them at once, technically. Except, there we go. And if we hit accept, what does that look like? That's not terrible. Looking at this, yeah, that's from what quality pictures I can get. It goes in a little bit deeper though. My circles might be, well, I don't know. And it seems to be thicker as well, a little bit more guff, a little bit longer. Sketch one. So can we? Of course not. That's locked in there. Ah! Hang on. More messing about. Right. So in my sketch, I just made these circles 1 inch and lowered them even further, and I'm really liking a little bit more the depth on the lower end of the bits. So I'm gonna say scrub it and call that good. Let's put some fillets on here. Something like that, maybe. Yeah, that looks fine. Then we're gonna do some fillets on here. Now this is probably gonna want to complain at me because I got too aggressive, but we just told don't freak out. Go 0.05 on that. Oh, we can. All right, that's a nice round number. Lovely. Look at that. And then we're gonna fillet this bad boy on up here. And we'll just go oh, smashing, bro. Positively smashing. And then we're going to fillet this and what is it, 0.05? Did I say 0.05 or 0.03? 0.05 maybe. No? Yeah? Yeah. Yeah. There we go. Look at that. That's pretty banging mush. Yeah, nothing wrong with that. Just need to cut out the slot for our lever. Right. So we go to here, and this is 0.06. Ooh, what was that? Crap, I don't remember. Here, let's just do 0.06 for now. To mention this up, I'll figure out what the maths are here in a second. 0.06. Just, oh no, it's 0.6. 0.60. It's 0.60 donkers, and this could be 0.125. I don't know. 1/8 of an inch. Bish bash bosh. And then I need to go get those numbers though. Yay! Okay, so we did have that right, actually, but these are they're not construction lines, they are real. So we need to do that, and then click on here, and we're going to extrude that. We're going to remove it. Uh-oh, I'm just having another moment. I'd say a good 1/2 inch. Yeah, let's do that. Booyah. Okay. I think that'll work out nicely, honestly.
You know, actually, we could actually put that into our assembler and see what it looks like. Now, these are curved. I realize with what we're doing, we probably shouldn't have these as curved, but whatever.
Insert. Technically, I called it the throttle knob, but whatever. I'll fix that later.
That's just housekeeping nonsense. Okay, so let's see. Can we grab the top bit of the knob? Doesn't look like it. Let's see if we can grab that side there. And maybe grab that side there. And that did something. We're a bit off-cent. No, are we? Yeah, what the flip happened? Yeah, we need to be... Oh, yeah. Oh, yeah, for sure, bud.
Offset. Can we just flip primary axis?
Yep. Okay.
Hey, actually, it looks almost a little bit small.
That's what she said. But that will give us enough clearance. It almost doesn't look wide enough, honestly. If we look at the photos,
such as here, those knobs look a little bit fatter.
Here's another side view, and yeah, that knob looks a little bit fatter, to be honest. Interesting. All we go is back to our first extrusion, and we'll just go like 0.6 inches. Fatten that bad boy up. Now we'll see what it looks like.
That looks a little better. That looks a little better. Yeah.
Okay, so this is going to be the throttle knob. Again, we'll just select the right because, yes, I'm always right.
Absolutely, darlings. This one's going to be really easy.
How big is the knob? Let's go 1.3 inches.
I'm literally just pulling that out of my you-know-where again.
Up the exit. I'm pulling it from my exhaust pipe.
Yes. Oh. And extrude that. Let's just
go 0.4 inches.
So just under half an inch, I guess. Again, I'm just guessing. There's a little poke. And then we'll just do a fillet on both sides. And let's do you think it's like this, or does it all round out like a tire? Like a toiga. Back up a little bit more. There you go, honey.
Okay. What do you think? Let's take a look.
Zooming in here, yep.
That looks a lot thinner than this knob, so take notice. The mixture knob looks like it's the same thickness as the prop knob, but this is definitely a lot thinner. But that diameter, we may have to make that bigger, honestly. Should we make it bigger? I don't know. Yeah, I'm not sure. Let's just go ahead and I need to cut out R. I need to sketch on a plane that I can think. Let's see here. Sketching on a curved plane sometimes takes me half a second to grab.
Top plane. New sketch on top plane.
Remove that, and now you can see. Theory. I hope this should work.
Let's do line and center line. Let's do this. Okay, yeah.
It's fine. That's fine.
This is fine. Everything is fine.
And our dimensions again are going to be 0.06 for the length. Holy guacamole, Batman! Oh, because this is defined. Yeah, we're gonna cheat this a little bit. 0.06. That's that. No, it's 0.6. 0.6 freaking donkus. So points, but that's, yeah. And then the width is going to be 1/8 of an inch, 0.125. That's the width of a rod. And oh, this thing's going to aggravate me. Much aggro. So I need to, I'll scrub it. You know what? I'm gonna eyeball it. You should not be doing this, but this needs to stay like here. Fine. Thank you. For goodness sake. Oh shoot. But then again, this is not. I need to select this. Oh, that's why. Yeah, drawing on a circle can sometimes be a pain in the bahooty. Know what I mean? Know what I mean, brov? There you go. Now I can click on there. And then we'll go to extrude. We'll go to remove. And then we're going to bring this back up. I mean, we could do that. If it doesn't like me adding stuff, then fine. We can add that to there, and then we can go to here. This is a very, very ditzy way of doing this. But then we could slice it in there. 0.5 inches, or actually 1 inch. So it goes in 0.5. That's a very, Alright, well, we could do that, and then we just go to extrude. We could do this, and then remove 1 inch, boosh. A bit of a dirty way of doing it, but shh. Anyways, no must fuss. Okay, there's our prop. Excuse me, our throttle lever. Go ahead and import that into our assembly right quick. Throttle. I do like a good throttle knob. You know what I'm saying? Way. I don't know what I'm doing. Fasten mates again. We'll go to center here, and we'll go to center of here, I guess. Whatever. Oh. I love it. Love it. How do I need to... How do I must not have chosen the right hoo-ha.
No, I didn't choose the right hoo-ha.
Reorientate axis, and then... Guys, if this doesn't work, just start freaking pushing buttons till something happens, okay? There you go. There we go. Now we got it. Now we bloody got it. What? Oh my goodness. Okay, yeah, I have that, but it's exactly... Yeah, okay. Don't go right. No? 180? Hey. There we go. There we go, because now we can see our cutout there. Bish, bish, bosh. Like so, I'm thinking that knob is actually way too flippin' small. That thing is freaking tiny compared to the prop shaft knob. But if we look in here, yeah, that knob is just as girthy as that one. What? So let's fix that right quick. Who doesn't like a bit of guff? We'll go sketch 1. Let's start breaking stuff. Let's do 1.6. Let's start breaking everything. Oh, wow, I did not break it. I was getting nervous when I'm doing stuff like that. Oh, it got bigger.
That's what she said.
Still too skinny of a profile. More extrusion is necessary. 0.4, let's just do 0.6, because, yeah, I'm feeling generous. You mother trucker.
Oh my gosh, I cannot hit my switches anymore, people.
No one's watching this crap anyway, so it don't matter. Oh, now we broke it. Well, let's just see if that's just the right size. Yeah. I think that's a bit more respectable. Yeah, I think so. Let's clean it up here for a second. Guys, hang on. Yes. And you can see his hand here. I mean, that's all right, here. You can see, yeah, that's a fairly big knob. But we can see the prop mixer knob's a little bit smaller than these guys. Okay, fair enough. Cleanup time. And assembly. Assemble! Autobots assemble. Okay, there we go. That's alright. That looks a little bit more to scale, eh? I think so. I think so. Yeah. Nothing wrong with that. I think that'll work. Yeah. Alright, last one is the mixture knob. Now, truth be told, I kind of already hashed this one out. So here it is. Remove the planes. So basically, it's got 6 pointing grabby thingies. Textured, tactile knob. Bits of knob. I don't know what the freaking heck you call these things. I believe there is 6 to a side on these. As you can see right here. Although, admittedly, it is a bit blurry for you guys. I'm sorry. Now, with this knob, I bashed it out offline because it took me a little while to figure it out. However, I think this knob might be a bit too small when I first started working on it. I got it at 1 inch, which actually 1 inch may not be too bad. So I drew a circle, extruded that. You get your cylinder, lovely cylinder, and then I drew another plane, which is basically on the more or less on the surface of the knob. Then I made another sketch. You can see where I made the. You can see where I just made that plane. That's this lighter color here, and this dark blue color is what I drew on it. I drew a little square just beneath the surface on here. Then I created another plane, a little bit off the circle area here. And what that allows you to do is that allows you to create a coincident point, and then you can stretch what you drew here to here, and then you go to loft here, and then that sketch you saw, that blue triangle, which you can see in yellow now, you select that, and then you select where you want to pull it to, and in this case I want to pull it to that dot, and it creates this little triangle pattern, and you hit OK, and you go, yay! And then to put them all the way around, you just for OnShape, it's called circular pattern tool, and then you say how much you want to rotate this around and how many knobs do you want. In this case, we want 6 knobs. If we only wanted 180 degrees, we type in 180 here, and you can see it'll still put in 6, but it'll only put them at 100, or it'll only put at 180 degrees. We can go 360, you can do 360 degrees. If you want 12 knobs in at 360 degrees, you can type in 12 knobs. If you want 180 knobs here and you want 7 instances of your drawing, then you go over here and you get 7 instead, or 2. You know, well, there you go. You gotta get enough of them in there. But anyway, so it does look like it does do 360. It does appear to me from the photos I saw, there's 6 of these little grippy thingies. So that's what I settled on. The last thing I have to do, though, however, is punch a hole for our lever to go through, and then we can see how well it looks on OnShape. It does. There looks like there is a slight fillet at the end of the knob, so we'll see if we can't model that in. Oof. I really hope OnShape won't get too cranky. In fact, let's just try that right now. Oh, good. It won't get too. Ooh. Yeah, but then you see that our drawing, we start to have some overhang with our knob section. So, I may have to tighten that square up a little bit, which is not a big deal. All right, so how are we going to sketch this? We need to bring our planes back up here. I want to sketch on this plane, please. So in theory now, I can... There we go. Okay, excellent. Thank you. Again, the width of this thing is going to be 0.125 or 1/8 of an inch. I can't remember what Send Cut and Send does because this thing, I literally spent months on this project. So I may have to revisit these numbers later. I don't know. 0.6 inches there. And then we're going to go to deselect that. And then we're going to select our triangle. And they're going to extrude that bad boy. That boy mudder. And we'll go depth. We'll just do 0.6 inches. And hit enter. Okay, there's our knob. Yay! Let's put it in on OnShape. Let's put that into the assembler. Yeah.
Insert. Where the flip is the
knob. Holy guacamole, that is way too small. That's what she said. Wow, that's just not. I know it's smaller. I don't think it's that freaking small. Well, let's put it on here and see what the damage is. Rotate. Looks like it's stuffed in the hole nicely. Whee! Yes, shut up. Just hush. It is smaller. We did say it's smaller. Let's take a look at here. Okay. Envision that for a second. Now, oh, that thing's way fatter though. It's fat like my ex. Hey! Yes, we do X jokes here. That thing is way too small. How about the diameter? I mean, oh gosh. Yeah, that's pretty weak. That's pretty anemic. Yeah, that's pretty anemic, isn't it? What's the extrusion on that? Anyways, let me model this up a little bit better, guys. You see how I roughed it in. Let me go ahead and I'm going to model this and see if I can't tweak it right. So, put on some couple right tunes. Be right back.
We're almost done, I promise.
We're almost done.
So at this point, I do have the blueprints. And they're still an incomplete set. They'll never be a complete set, just due to revisions over the 30, 40 years. But I found, I don't know why I missed it the first time, but actually I found all 3 levers, prop, throttle, mixture, all detailed in their actual dimensions, as well as the knobs. All 3 knobs, I had enough dimensions to actually model an accurate scaling of them. And I was peeved when I found them. Like, now I gotta go in and redo all my numbers again, which it only took 10 minutes. It wasn't that bad. Let's take a look and see what I found for the blueprints. The missing blueprints. So you guys have already seen this one. This is the mixture control lever, which I based everything else out of because I didn't have anything else to base it off of. By looking in the archives and we have the RPM and the throttle levers. And as you can see, they're all ever so slightly different. The RPM lever is 7 inches long. The throttle lever is 7.6 inches long, and of course the mixture lever comes in dead last at a whopping 6.5 inches long, basically. So with that, I have the full trifecta, the whole Pokemon collection as far as lever collection is concerned for the blueprints. This was really awesome. So we'll go ahead and plug all of this in, and then for the same levers, I found all 3 knobs. Isn't that cool? Let's zoom in here. So this one is the knob for the throttle. Very, very handy because it was getting hard to eyeball it. And as we can see here, this knob is 1.5 inches wide and it's 0.75 inches in width. This is very hard to see sometimes. I had to actually, I don't know, I think it was the prop one. Actually, I had to draw lines because it's faded pretty bad. But, so there is the throttle lever. This is the RPM, or your prop lever, if you will, prop knob. It was about, 1.3 inches in length, I guess. 8.88 plus 0.88, I think that's 1.2, 1.3 inches. And the width is also 0.75. I'm like, all right, sweet. And then from here, believe it or not, see that? 0.31 radius. We actually have a measurement on the radius. We can accurately make those divots in there as well. Fantastic. And here is the knob for the mixture control. Yes, this is one that was really messing me up. Again, common theme, 3/4 of an inch width and diameter. How cool is this? They even show you the degrees on the actual knob texture grab piece. I don't know what you call that. They actually measure the degrees on there, so you can actually accurately reproduce that. I'm not gonna get that crazy. I'm just gonna use a Boolean tool. Looks like it's 1.25 inches in height. So it is definitely a little bit smaller, but it is 1.5 inches. I think that's 1.5 inches, 1.5 inches in width. That way. Anyways, it just made my life a whole bunch easier. I don't have to go print one up. I don't have to eyeball it. We know that these are the specs. Fantastic. Let's go ahead and plug all these numbers in and see what it looks like. As for the tensioner knob, we unfortunately, if there are numbers in here, they were deleted. I don't think they were because this just shows you where the hole goes for it. But at least I have the general pattern for it, and based off all the other knobs, we can pretty much guess what this should look like to scale. All of the other 3 knobs are going to be to scale, so this we can actually just make up and put it into the assembler and see if it looks scaling wise, if it looks like the right size. Basically, that's all we can do. But at least we have the pattern here that we can go off of. Sweet. That's technically labeled the handle for the friction dampener adjuster. Sweet.
Wow, I just realized my microphone gain was turned way the freaking heck up, so yeah, this channel's not monetized, so I can officially say I'm not a professional on this channel, at least. Anyways, here we are, Bish Bash Bosh. I got it all sorted out thanks to the freaking blueprints I finally was able to unearth in the old archives. I still don't have the blueprint for the main console here. I don't know if I'll ever get it. We just may have to run with it as is, although it's pretty close enough. I don't think I'll have to worry about that. Draw your attention to the knobs. I got them all dialed in. I went and dimensioned every single flipping one of them. Mixture and the prop and the throttle, and I can safely say this is correct, at least for the 1951 Beaver. At least that's where most of my blueprints seem to have been sourced from, was from 1951. Also, I took all the diameters of the shafts here, here, and here. I plugged in the new numbers, and this is a final result of what you see here. So if we watch the throw on the mixture one, mixture throw looks good. Prop lever, or RPM lever if you will, looks good. I like that sweep. And the throttle sweep, again, looks good. Fantastic. And if we scroll down here, we've got tensioner wheels. Yay. Came out pretty good. I'm pretty happy with them. They do protrude, as is correct, a little bit from the throttle console. So when we swoop the throttle all the way down here, there you go. There's a little bit of visual for you where we're at. They look great. It was pretty easy to make. I just simply started with a sketch 1, and we get this little flower power dealio. Basically, I made the main circle of let's see here. Where's it? One. I made it 1.6 or 1.65. No, 1.8 inches, so almost a 2-inch knob, if you will. And then I made one circle here, and then what I did is I simply went to the circular pattern and made it go around 360 degrees, and I said I wanted 8 of them, and that's what spits me out. And then what we do is we hit the extrude button. That's the extrude button. That's the second step. And then I made another sketch. This is where I start to, there's a little ringlet that goes into there, into the knob itself. A little designer piece there. And then, of course, sketch 3, I made the hex bolt where the hex bolt's going to get lodged into to actually turn the actual shaft that goes into the console. And then I extruded that. And then what's sketch 4? Sketch 4 is just extruding this piece out here. And I don't have the dimensions on how thick this is. So this part here, I'm just eyeballing it with the different videos that I've found. But it looks pretty good. We could put I'll probably put a little chamfer on that. You know, you just click on this button, I think, and then you can go, or not chamfer, fillet. And we'll just pull this back and see. I don't know how well it's going to like us to. Oh, there you go. There's a nice little fillet. Yeah, just a nice little round piece, so you don't have to cut your. Well, you won't be cutting yourself as plastic, but just a nice little fillet to help round things out. And we can do the same on the other side. There we go. So it's a little bit more well-rounded. That looks all right. Go back into here. Wait for it to update. Maybe move a lever here and they'll get updated. There we go. Yeah. There you go. Sweet. Well, you know what, guys? If I get the dimensions for the throttle console before I print this, I might re-engineer this a little bit. But what I can gather, this console is basically 9 inches wide. I've seen some doing some maths for all the blueprints I do have on the center console piece. I can't remember what they call it on the actual blueprints. It looks between 8.5 and 9 inches, so this is pretty much as correct as we're going to get. The only thing that is not quite correct is our tensioner knobs. Technically, they are offset with the real airplane, but they're on the other side. They need to be moved over about 3 inches, but I'm not going to do that because I really don't feel like re-engineering all of my lever bearing supports. It's gonna be a little bit off, but I don't care. You can see how much work I put into this already. I don't care if they're a little bit off. I got 3 knobs. They're offset, just in the wrong direction. The sizing may be a little bit off, but I think judging how big these are and how these are, I kept them pretty close. Honestly, I think it'll be all right. There's going to be a little bit more buttoning up to do. I got to punch in some holes so we can mount this to the lower console deal. I'll do that later. But I think the AutoCAD work is mostly done, and we are pretty much ready to print this bad boy out. Fantastic. Wonder how much resin this is going to cost me.
And it will cost a lot of resin indeed, but I'm going to love it. It might be a while before I upload the next video. I have a Uniformation GK2 resin printer, and it's got a very small build volume on it. I think it's 5x5x9 or something like that. Or 8x8x5. It's a very small printer. And to print something of this throttle console, I think I measured, I made it 9 inches wide, it's like a foot tall. I need a large 3D filament type printer. The people in China, the manufacturers in China that manufacture the UV LCD for the resin printers, they're always very small. No one makes a huge, gigantic one, which could be fun. Could be challenging to print too. I don't know. I don't know if that's technically impossible with all that weight. If they'll come off the platform, I don't know. But I have to get a dry filament printer, because eventually also I'm gonna have to print up the dashboard. That's got your 6-pack gauges and all the stuff all the eye candy you see right in front of you on your instrument panel. I got to print that up too, and that's just way too much work. I calculated it out. It'll take at least printing my throttle quadrant up in 6 pieces on the resin printer, and then you got to splice them all together, glue them, and then they look a little bit odd. It's just a little too much hassle for me, so I have to save up for a large format FDM printer. There are a few guys local in my area that might be able to print it up too, but regardless, we will capture that printing and assembling it. I also might do the tin work on that video as well, showing you the throttle label. It's a black placard, 10-piece of placard that bolts onto the throttle console. I might show you guys how I designed that and print that up as well. This is the DeHavilland Beaver wraparound logo as well. But I think this video will help at least hopefully inspire you guys and at least put a good solid video down as on this build, and hopefully attract a few viewers, and hopefully you guys will like it, inspire your own to do your own rig builds. It's gonna be a lot of fun, and thank you for watching, and stick around for more. Peace out, Girl Scouts. We'll catch you on the flip side. I'm gonna do this.
Well, I'll wait for work on that. Let's do some fillets over here, eh? Oh, is that why you're complaining? Oh, my dad. Oh, easy. Lay off the caffeine there. Come on, Point. Come on. What do you mean dimension cannot be added? We're on a plane. What? Oh, easy. Run muffin. What's this all about? And then you select the entity that you're splitting. Entities to split with would be your split here, the gray bit. Hit OK, and it does not work. Let's try this again. No, I didn't want to do thin. Oh my goodness. I wanted you to add. Create from nothing. Here, select, extrude. New surface. Boom. Why did... popping off. Right, we're here at the live cam. I actually printed part of the throttle console up. Let's go over the left. Aircraft selector. I'm such an idiot. Load you from the Cockpit computer. Hello. Come on back now. Come on back. Oh. Lag. Lag you wee much? Hello. Oh. Looks like we're gonna spawn in. Oh. Lag. Ooh. My poor computer's about ready to throw in the towel. It's like 10 years old. I'm surprised it can even run this in the first place. Let that bother. Well, someday the rest of the plane will load. Right. Oh. Hello.